morning, everybody. Or evening, good night, good afternoon, depending.
Yeah, we have a big variety of time zones represented.
Morning, everyone.
Hi.
Everyone's sufficiently caffeinated for the 4-hour show.
Unclear. We'll see.
Yeah. We'll have a break.
Got my cold brew here to keep going.
Yeah, I sank a pint of cold brew earlier, but I don't know if that was enough. We'll give everyone a couple of minutes to get in.
No, we were excited during the ISCE science team meeting to hear about how they're going to turn on the radar this week.
When's first light? When's the first image?
They hope to actually acquire an image on Friday.
Awesome.
I'm not sure if that qualifies as first light. We'll see if that's going to be a released image, but it's going to be first collects on Friday.
Yeah.
Just so.
It won't be a complete image because the satellite's not in the final orbit, so they have to turn off like most of the beams, so they don't, because they won't be overlapping correctly. They can't do the full beam forming, so it'll be an image that's only partial image, but
Like I care. I would love to see something, that so that it's working.
My ISCE is ready.
oh, you got the whole model. That's nice.
Did you not get one of those in India? I broke my reflector.
I didn't go to India.
My reflector was not resilient when this was from a year ago or so. When I put it in the suitcase, the reflector broke.
We're up to 60 people on the call, so maybe we should start. So good morning, everyone. This first hour of the morning set aside for questions and feedback from yesterday. I don't know if anyone has anything they'd like to show, for example, about their modeling or their interpretation of the interferogram, or any questions that arose from the theory lectures. Any of those things would be great to ask about. We have the Q&A box, obviously, and you can also stick your hand up and speak live and potentially share your screen and show us what you've got.
Yeah, I'm curious to see if anybody got good results with the depth versus volume change estimates and a nice misfit plot.
That was the tough part.
There was, yeah, if you're not used to the Python programming, and then there's lots of stuff. You have to set up your search space correctly and the step size. There's lots of difficulty. But yeah, if anybody has questions or has results they want to show or not sure about the results, we can look at those.
I like long, awkward silences, so we can sit here and wait until someone says something. That's great.
There were a lot of questions in the office hours this morning.
I assume not everyone was able to make it to those, so.
Also, if you think your results are great, we'd love to see it. Shy crowd today. Let's see.
Okay, so Ali Reza asked the question first, and then Camilo has his hand up, so he'll go second. Who wants to answer Ali Reza's question?
Yeah, so it does.
You maybe repeat the question for the purposes of the recording.
Yes, so the question is about reference points in interferograms. So because interferograms are a relative measurement, it shows you changes of things in space and time. You need to provide a reference point at which you believe you know something, either a deformation or topography or anything. And so that is also relevant for phase unwrapping. You would like to start phase unwrapping in a place where the phase is reasonably reliable. Say, yesterday we looked at an interferogram of Okmok volcano. It's an island. You don't want to start phase unwrapping in the ocean. So typically we use some sort of a coherence threshold to decide where to place the reference point for unwrapping. But mostly interferograms are getting unwrapped individually, so they all initially will have a different reference point. But then when we analyze them in time for a time series, we pick a reference point that's common to the stack. And I see Eric is typing, so he may have additional thoughts. So you don't actually have to do anything. The software like ICE is doing that automatically for you. So you don't have to like manually pick a reference point for unwrapping, but it's being done internally.
We had two people with their hands up, melted away into the into the darkness. Ah, Florian, there you are. Do you have a question?
I didn't really have a question, more in response to your question whether we played around with the Mogi source function with the modeling. I did that this morning, and one thing that I noticed is, I mean, obviously very very nice code. It was working flawlessly without me changing anything, fortunately, and to do the changes was very understandable as well. What I found a little, I don't know what word to use, like funny, was that the volume and the depth were already specified with to a very high degree of precision. So I was playing around a little bit both with like just um, around that depth that was provided already to do very small steps, or and a very narrow depth range and volume that I was looking at. But also I realized then when I plotted the misfit map that it would give like it wouldn't cover a big area. So I noticed that you kind of already need to know a little bit about where your thing is, or you need to like boil it down by trying out a lot of things, a lot of depths and volumes, or it takes a lot of computational time to do a large range of depth with very low little increments, which I kind of tried to try all three of them, and I think I got to a satisfactory result, but it's just something I noticed. And I wonder, like, when you really process these kind of, or when you really interpret these kind, or create the models more than, like, how do you start off at a certain point, I guess, just how I described that you do a large range with big increments or something like that.
Yeah, both when you do grid search, but also when you do any kind of nonlinear least squares, you need to know a lot about what sort of result you expect sometimes the misfit space. So for both of these examples that we're looking at, for the X versus Y and the Z versus volume change misfit function, the benefit of them is that they have a very clear defined global minimum. But sometimes these misfit spaces are very nonlinear, and you may have a global minimum, but also more local side minima. So starting in the right area will help you converge to the right place. Also, what you would do if you do grid search in an actual environment where you don't know exactly what the depth is, etc., is once you have a solution, like in these plots, you get the misfit function and you get the location of your best solution. And sometimes if you set up your search space incorrectly, your best misfit is at the edge of your search space. Say it may be at the shallowest depth that you search through, or the highest depth that you search through. That's an indication that your search space is set up incorrectly, and you would iterate and move it, if that makes sense. So looking at where your solution is relative to the search space that you span can help you. But it is tricky. You have to find the right extent of the search space, but also the right step size. You don't want to oversample too much, but you also don't want to miss the minimum. So it's a little bit of trial and error involved.
And usually you start coarse and sort of focus inwards if you don't have any other intuitions about what you're doing. Or you make some forward models and you see, oh, that's too big, that's too small, kind of eyeball it.
And you're right in this case, because so also what you could do is you could search for all 4 dimensions at once, right? You could span up a 4-dimensional search instead of what we did, where we fixed 2 and searched for the other 2 and so on. But in our case, I intentionally kept the solution very close so that in your X versus Y search, you don't end up with like huge, misfit and like I could have set up a different depth for X versus Y, and you would get much larger misfit because the model wouldn't fit the data as well. So I kept it reasonably close for the sake of this exercise. I think Gareth is going to do a much more sophisticated grid search exercise later this week.
Today.
Where he's going to randomize, starting points and so on, and crowdsource the exercise a bit. So you get a bit more of a feeling for it today when Gareth is going to work with an earthquake modeling exercise.
Right, there's more questions in the Q&A.
Oh. Yes.
Read them out.
Amrit asks about, I would expect InSAR uncertainties to increase with distance from the reference point, but how do they vary with elevation? So the reason why Amrit is saying that is because he has a lot of experience with sort of turbulent atmospheric delay, which is often a driving source of distance-related errors. So at the reference point, you basically pin everything to a known number. And then from that point on, errors increase with distance. They do for a variety of reasons. One of them is phase and wrapping errors, but also error sources that are scale dependent. Atmospheric delay is scale dependent. If you have 2 points in an interferogram that are close by, they will look through a very similar atmosphere because the atmosphere changes not dramatically from point to point. In the way atmospheric delay sort of gets more dissimilar is as a function of distance. And so the further you are away from a reference point, the larger the errors are going to get just because of turbulent atmospheric mixing. There is also atmospheric delay that relates to topography. And so you can also have errors that are creeping in that relates to the difference of the elevation of the reference point relative to the difference of another point within the scene. And so both of those can appear. Eric, fielding in your, or we do a MinPy exercise. I can't remember if you're looking at the landslide in this case, or if you're looking at some other phenomena, but Eric Fielding has a landslide case in California where you can see a little bit of both. When you look at the errors in the phase estimates, they increase with distance, but there's also a component that increases with elevation difference.
That's more of a time series result, though, rather than an individual interferogram, right?
Yep.
It affects individual interferograms, but it's harder to quantify.
Okay. Does anyone who's actually asked a question want to ask it out loud? Because otherwise we just have to read your questions out loud. It might be better if you ask them yourselves. Don't be shy.
Answer your question. Ask your question.
Okay, Camilo.
Yeah, thank you. So, of course, as you guys were saying, the size of the grid and the space that you're going to create, well, has to match with the with your proportions of computation and whatever you're trying to model. Are these dimensions correlated to your SAR sensor? I mean, if the minimum resolution that I can get is, let's say, 30-meter resolution per pixel, and I'm mapping, pixels of 5-meter or 10-meter on my model, maybe like I should map or create grids above this resolution of my SAR sensor. Like, is there any maybe recommendation on maybe not making your model that fine if your sensor that you're using to interpret that is not as precise, I guess.
It's very rare that your model is going to really cap out of the resolution of your data, I think. Normally the signals that you're looking at will have a larger spatial extent than a pixel or two. And that's only when that'd be when it really mattered, I think, to consider this resolution of the sensor. Normally these signals are spatially continuous over hundreds to thousands of meters, and your pixel size is of the order of 30 to 100 meters or something. Franz, you
some
were going to
ways-
say
Thank you.
something?
Yeah, in some ways, whenever we interpret InSAR data, you saw yesterday already that there are lots of error sources and interferograms that we need to deal with. In order to separate the signal that relates to your geophysics from other components of the interferogram, we kind of have to assume that there's some oversampling that is happening where sort of neighboring pixels are related geophysically, both in space and in time. Also, when we do time series analysis later, we sort of assume that the temporal sampling we get from the InSAR data is higher than the temporal variability of the signal of interest. And that will allow us to model them, but also to use the sort of redundancy we have in the system to do some mitigation of error sources, such as atmospheric delay and phase unwrapping errors and other things. So it's almost always assumed that the physical characteristics of the signal that we're interested in has resolutions in space and time that are, or variations in space and time that are smaller than the sampling.
There's 5 more questions in the Q&A. Anyone want to ask their question live? Stick your hand up if so. There's a raise hand button under React.
If not, I can always just read them too.
Enrique, unmute
Yes,
yourself.
thank you. My question is more about NISAR. Using 2 bands, L and S band, what is the expected for reducing atmospheric noise or improvement of coherence? What is expected of this sensor regarding to that? What software we will use for processing the data? ISCE or what is the workflow that we will use? And thank you.
Yeah,
I can answer that. So ISCE3, yes, will be necessary to process the NISAR data, but NISAR will also be producing level 2 data products that are basically ready to use without further processing. You can load them directly into a GIS, including geocoded unwrapped interferograms and the geocoded radiometrically terrain corrected amplitude images, which NISAR calls a GCOV. GCOV. It's a covariance between the different polarizations. Yes, if you want to do your own processing, you're going to need to learn ISCE3. We don't have a full ISCE3 tutorial in this short course. We're going to have an introduction on Thursday, but there'll be a new ISCE3 tutorial later this year or early next year.
Eric, is there going to... Oh, sorry.
Becomes available.
Is there going to be simultaneous LNS band acquisition over places?
Yeah, so the S-band data is going to be limited compared to the L-band data. The L-band data is going to be collected over all land where NISAR is passing over, basically all land except the very, very tip of Greenland and Svalbard, and a little hole next at the South Pole. But the S-band has a lower capacity for operations, and they're going to be covering India and the whole and adjacent areas in the Indian subcontinent, and a few other places around the world where we have special calibration sites, including California.
And the original part of, or the early part of Enrique's question, I think, was what can we do with the atmosphere? And I assume the ionosphere is the thing that you will be able to characterize best out of all these atmospheric noise sources, because there's a big difference in wavelength, and if you're acquiring at the same time, you really should be able to solve for the ionosphere very well.
Yes, where you have both the S-band and L-band, you'll have an excellent, extremely accurate way to measure the ionosphere. But NISAR L-band already has two separate bands. It's going to be acquiring data with the main band and an extra band, and the difference between those bands can be used to calculate the ionospheric estimate very accurately. And this is a completely new feature that hasn't been done on other satellites. And we think it will be extremely effective in estimating the ionosphere just from the L-band data itself. And that will be included with the geocoded unwrapped interferograms, will be the ionospheric estimate layer.
Yeah, so it's going to be included as a separate layer that you then can apply if you want to, or
Yes.
choose not to. For tropospheric delay, natively, there isn't necessarily a benefit because the troposphere is not dispersive, so the delay is in sort of meters units or in some sort of a length scale unit the same. But who knows? I mean, there is an interesting feature in ISAR is that the L-band and the S-band radar will look at the ground slightly differently, with sort of one PRF forward and backward squinted. So there's some multi-geometry components that people could start thinking about for potentially better atmospheric correction. So you look through the atmosphere a little bit differently in the two wavelengths. Whether or not that's going to be large enough to have any kind of benefit, we don't know, but it's worth investigating. And then the L and S-band data in some places, it's really interesting to see what kind of scientific benefit it has to have both of these wavelengths available. There's not a ton of experience with S-band on Earth. And so what you will gain by looking at ecosystems or by looking at deformation phenomena in those two frequencies, it's going to be interesting.
There was the experimental satellite NovaSAR S that was launched by the UK. And then I think it's now like largely operated over Australia. But other than that, there's been very little S-band data acquired by satellites.
Massif, you have your hand up.
Yeah. How much the NISAR would be sensitive to deformation?
Well, I mean, it will be sensitive to deformation on scales of centimeters and larger, probably. L-band obviously has a longer wavelength, so like you dividing one phase cycle into pieces, you're not going to see the tiniest of deformation so easily with it. But usually the sorts of things that we care about have deformation signals of millimeters per year or so, and part of the specification is that NISAR should be able to detect those. That's one of the things that in the validation of the data that we will be checking is true. Again, like someone on the science team, like Eric or Franz, will be able to say more about that.
Yeah, and it's always a trade-off between interferometric coherence and interferometric sensitivity. Like X-band, you would expect, because it's a 3 centimeter wavelength, is much more sensitive to very small displacements, but it usually decorrelates in a lot of the places that we care about. So L-band's benefit will be that it's going to provide coherence in places where you just currently don't have any with missions such as Sentinel-1. Eric proved that recently, even though Gareth had also a good C-band interferogram. But at L-band, even after 2 years, the coherence in many natural environments is still really, really good. So that it can allow us to form interferograms that are they have longer temporal baseline, which increases the ratio of displacement to other signals. And we just can measure displacements in places where we currently cannot. So on a global scale, I think that NISAR is going to provide lots of super useful data and more ability to look at land displacement than you currently get with Sentinel-1. Depending on how long the mission is going to be funded for, we heard earlier today that we have, in theory, capability to run the mission for many, many years. Depending on how long it's going to be kept up and running. If you have very long time series at L-band, I think we can do fantastically interesting stuff at high quality in lots of places.
Yeah, as Gareth mentioned, there is a science requirement that for NISAR to measure small deformation, and for the gradual deformation that we call secular deformation, it's 2 millimeters a year, but once we have 3 years worth of data. So that's not something you can measure just with 1 year of data, but after 3 years, we expect to be able to measure 2 millimeters a year of surface displacement. Of course, in 3 years, we'll also have around 65 acquisitions. And that's going to make a big difference in averaging out the noise sources such as the atmosphere. So there's a question here in the chat from Baruz, who was a visitor at JPL some time ago. He's asking about how do we define reference points if we're doing several different tracks in an area? And is it possible to use the same reference point for different tracks? The only way you could use the same reference point for different orbit tracks would be if they overlap. This is a problem where you may have to do some kind of balancing to adjust the relative phase for different tracks if you're trying to use multiple tracks to cover an area.
The tracks typically overlap by 1/3. So there will be a sort of a zone, one subswath where you get 2 tracks covering that same area. And yeah, you can subtract the value of the interferogram at a point that's in both and set that same point to be 0 in both interferograms. The one thing that's going to be an issue is that the incidence angle of the radar will be different between those two, and quite different. Like Sentinel-1's incidence angle varies from 30 degrees in the near range to about 45 degrees in the far range. So that 15-degree difference means that if you have a large deformation signal, particularly, it might not be represented the same in the 2 interferograms, and they will look like there's a join in your data set because you won't be able to make them match perfectly if there's deformation. But maybe that's not a huge problem. And you're still making real measurements. The measurements in that zone are both correct. It's just that they're seeing a slightly different view of the same deformation that you might have.
Yeah, you may be familiar with a service like the European Ground Motion Service or the Opera displacement service that is ramping up. So those are very large-scale InSAR-based services. The European Ground Motion Service does it for entire Europe. And they do provide a seamless product. The way they do this is they use InSAR to really focus on the localized, smaller scale, sort of 100-kilometer scale or so displacements. So what they do is they filter the InSAR data sets to remove long wavelength larger than a certain cutoff wavelength, maybe 100 kilometers. I don't know what the number is, signals, and then tie it to the GPS record. So they create sort of localized displacement maps on a European scale, and then anchor those displacement maps into the background GPS-based displacement record. And this way you can remove sort of offsets between interferograms and so basically use the small scale smaller scale, 100 kilometers and smaller from INSAR, in the larger scale from GNSS. There's a question by Amo that sort of is in your wheelhouse, I think, Gareth, about grid search and whether grid search is applicable only to volcano modeling or also to other applications.
I love grid searches. They're good for lots of things. It's the simplest model, the simplest search of parameter space you can run. The only issue with them for some models is that there are too many parameters to search for efficiently. It works well for Mogi sources because there's only really 4 things that you can change, and even a 4-parameter search is actually starting to get quite a lot of computations because it's an exponential increase in computation time every time you add another parameter. You raise that power by another 1. So like a search of, if you did a 2-parameter search and you had 10 intervals, then it's 10 times 10 models that you would evaluate. If you did that for 4 parameters, then it's 10 times 10 times 10 times 10. 10 is that 10,000? Yeah, it scales really, really sort of alarmingly large over if you increase the number of parameters by a few. So that's why we don't tend to use them for things like earthquakes, where there are 9 parameters that you could potentially solve for, and even in a simple model. There we've tried to use some other algorithm that does the parameter space search a bit more efficiently.
Yeah, and so what Gareth is going to show you later today is still a search algorithm. So it sort of steps still through that, solution space in some form. But it basically leverages, if you looked at these misfit functions yesterday, they have characteristic shapes. And there are algorithms that basically look locally at what the shape of the misfit function is, and then basically do things like step down the slope, right?
Yeah.
So if you want to get to the bottom of the valley, and so you can look at sort of what is the greatest gradient in that misfit space, and you can just walk straight down toward the valley this way.
Yeah, we like to think of the misfit as a landscape, and you're trying to find the bottom. Like the bottom is the place where the misfit is lowest, and like the 2 like coordinate directions are like parameter values. You can imagine that abstraction of your misfit. I like like those 2D plots you've been making of misfit, right? That are color coded with values. Like the minimum misfit place is in the bottom of the valley. But if you have a multi-parameter model, sometimes the landscape is not a simple just trough like that. There's going to be hills and bigger hills and bigger valleys, and maybe the place that you're starting is not going to get you to the lowest point very easily. So there are lots of tricks that we use to solve that problem, and we might get into some of those this afternoon. Mara, do you want to ask your question out loud?
Yeah, sure. Can you hear me?
Yeah, you're a little quiet, but maybe you can project.
Okay. I was wondering about this question in the homework. Should we produce like an elastic model using Okada, Pollitt, or any other formulation, or are we supposed to look for that online?
Oh, so for that homework, you don't have to make a model, though you could. That would be certainly above and beyond what we're asking for here. It's more that, if you know that there's a vertical height change that you can measure in the interferogram, you could do simple trigonometry to figure out how much that motion would translate into the fault parallel direction. The fault is dipping at 40 degrees. I think that's that's right. And you know what the height change is between the maximum uplift and the maximum subsidence. So if you think about a right angle triangle with the inclination of the triangle, the hypotenuse of the triangle being 40 degrees, and like what would that be? The sine of the angle.
Okay, yeah.
Being related, yeah. So you could calculate what the movement on the fault would be for that vertical step. That's really what we're asking for.
Okay, perfect. Thank you.
Is there a standard model for landslides?
Ooh,
No.
question for Eric. Right? Al Handwerker, if you were here.
Yeah, we do sometimes do models where we assume that the landslide motion is parallel to the surface and in the downslope direction as an assumption. And that is a popular way. If you don't have enough information to get the full three-dimensional surface displacements, then you can assume that it's in the take a topographic map, a DEM, and estimate what is the down slope direction and assume that the landslide is moving in that direction, and then make a model of the landslide motion based on that. But the best way to do it is to get full three-dimensional surface displacements, and that's really only possible if you have three different look directions, which we get with the NASA airborne radar called UAVSAR here in California, but we may be able to get in the future when we have NISAR and Sentinel-1, because NISAR is going to be looking south relative to the orbit, and Sentinel-1 is looking north relative to the orbit. By combining the ascending and descending and the north looking and the south looking, or right looking and left looking radar, then we can actually get the full three-dimensional surface displacements, and then have a lot more information about exactly what direction the landslide motion is happening.
Those are all still kinematic though, right? I guess there's no equivalent to MOGI or Ricardo, which is like trying to actually recover parameters about the landslide. Yeah, no equivalent sort of simple analytical model you can.
No, there's no simple analytical model, that's for sure. What we can do when we have the three-dimensional surface estimate is use mass conservation estimate and estimate what's the thickness of the landslide flow, which is a very useful parameter.
I assume there are granular physics models, but I'm sure they're not simple to apply.
Yeah, there's some. Usually we just assume that it's moving as a block with some amount of friction at the base, but then there's some landslides that have a lot of internal shearing. So that's not always a good assumption that it's moving as a block.
I met Patrick last week. He's a geotechnical engineer. I think he might have some suggestions.
He has something like the models that Eric is talking about. It's kind of like these infinite sliding block models. And yeah, like depending on what you're looking at on the physics, if it's an earthquake shaking, that could cause different dynamics in the slope system. So yeah, there are these models that a lot of like geotechnical engineers do use. Try to model that stuff. But yeah, just a comment on that. I did have a question though, if you don't mind me, if you don't mind me asking.
Go ahead.
Go ahead. Yeah.
Yes. So actually, so in regards to the homework problem, and I kind of asked about this yesterday, like in the Q&A. But I was wondering, like, so that area that you grayed out near the fault, like within 1 kilometer away from the fault, in that fault problem, like I guess what causes like what could have caused that decorrelation in that area? Like why can't we read the exact deformation? And then wouldn't that suggest that there could be much higher motion right next to the fault, like more than that total subsidence we measured? Like if we cared about that area right next to the fault, could it be much greater? And like how do you usually like handle that kind of situation?
Oh, that area near the fault, I think there's vegetation there, and there could also be damage there. And those two things would basically act to eliminate any correlation in your data there. There is a hint in the interferogram actually that those fringes start to become enclosed. If you look very closely at the sort of the largest deformation fringes, the ones furthest to the right, that they start to kind of curve round, which implies almost that you're reaching a maximum and then once you moved even closer to the fault, actually the fringes might connect to some of the smaller deformation fringes from before. I don't know if I'm saying that in a particularly coherent way, but we would expect actually from that pattern that the closer you get to the fault from the southwest, the deformation is starting to become smaller again. It peaked right where we see the sort of the final fringes to the northeast. I can't remember what the rest of your question was.
Yeah, I guess that's kind of what I'm referring to, because like as the fringes get closer and closer together, like you have this like higher rate of displacement near the fault. And so it looks like things just become blurry, maybe because of that, because it's such a high rate of displacement.
That does
It could be a
happen.
part of it.
That's not the problem here, probably, but that can be a problem, yes, that you actually start to alias your signal if you have too large a fringe gradient and not enough pixel size to actually resolve it. You effectively can't see anything when that happens. I think here we're right on the limit of what's resolvable, but you can still see it. But yeah.
Yeah, there's a maximum gradient, that sort of deformation gradient you can resolve, where you can't resolve anything where sort of the phase change between 2 pixels is larger than 2 pi, then the signal basically decorrelates naturally. That happens a lot if you think of like glacier motion, for instance. If you have an outlet glacier that moves through a valley, there's often a very strong gradient of motion from sort of the edge of the glacier toward the center. Right at the edges where you go basically from stagnant ice to really fast moving ice in a really short distance. And you can get fringes that are just too tight given the sensor resolution, and you decorrelate just from the gradient of motion.
And that's where pixel offset tracking is more effective. Another thing we're going to be covering later.
And kudos to Gareth for making a coherent argument about incoherence.
Thank you. That was really helpful.
We use pixel offset tracking for landslides because some of them are moving very quickly.
You know, I've seen pixel offset tracking for like lateral spreading caused by liquefaction. There's been some research in that, and I guess it is good when you have these like larger displacements, right, that are occurring. Like if you just have 2 scenes, you have large displacements in those 2 scenes over a local area. They said is where you would like want to use that.
There is, in theory, an approach. If you have very wide bandwidth, very high resolution SAR data, there could be a way of using offset tracking to even correct the phase and help with the unwrapping. With some of the modern sensors, such as the ISCEs and the Capellas, etc., and Umbra Space, these new space missions, they provide very high bandwidth, very high resolution SAR data, where you can actually then estimate offsets with an accuracy that's good enough to unwrap the interferogram. Where you get to an accuracy that's better than 2 pi, in theory, at the very, very high resolution and very wide bandwidth data. There's a paper that Richard Bamler from DLR once wrote that sort of looks at that trade-off between so the resolution and bandwidth of a system, and to bring together basically the amplitude-based offset analysis and the phase-based interferogram analysis.
What about this question?
There's a question in the Q&A from Enrique Fernandez. Will the NISAR mission be like Sentinel-1 with A, B, C satellites? At this time, there's no plan to have a next NISAR mission. It's not an operational satellite constellation like the Copernicus Sentinel program, Sentinel-1 program. But we are hoping to have a follow-on mission that will be compatible with the NISAR data.
The answer would be speak to your congressman and your senator if you're in the US and say how important this is.
Yeah, they have to tell the Congress to give NASA enough money to launch more copies of NISAR.
There is the follow-on mission is called the Surface Deformation and Change mission, if I remember correctly.
Yes.
And it's currently in the kind of the concept stage where people are coming up with mission concepts. One of which is launch another NISAR.
Could call that
That's quite an expensive mission, apparently.
You can call the next one even nicer.
Even nicer, yes.
Okay, thank you.
Right, we're coaching the time that we've set aside for a break, so that we have time for maybe one more question and maybe maybe a preview of what we're going to talk about for the rest of the day. That sounds good, doesn't it? So whilst you're thinking of your questions, I will share my screen here. Okay, syllabus for Tuesday. What we have is a module which spans basically 2 hours on TOPS data processing that Eric is going to lead, and TOPS is an acronym that means terrain observation through progressive scans, and it's the particularly weird mode that Sentinel-1 has for acquiring radar data, where it has a beam that sweeps backwards and forwards, and this is to produce better radiometric accuracy, if I understand it, which is a thing that people who use the radar amplitude care a lot more about than people who do InSAR. But hey, they're not all wrong. I mean, it's useful to have radiometric accuracy in your data. But that produced a whole set of problems for InSAR processing. You had to actually deal with this beam changing. You have to align the images very, very precisely. So the workflow that we have for processing Sentinel-1 data has all that built into it. And that's why it's a separate processing workflow all on its own, but it's probably the one that is most widely used with ISCE2. So that's the one we're going to show you. And once you know how to process data in that workflow, it's very easy to adapt the other workflows that are in ICE, one of which is called Strip Map App, which we've included as a supplement in this course. So that's from 11 a.m., which is going to be in 10 minutes, through to just before 1 p.m. And hopefully that is enough time for everyone to process some interferograms. And then the final session of the day after 1 p.m. Pacific will be the highly previewed session where I will show you how to prepare InSAR data for modeling and run some simple but more complicated models than we ran yesterday, but still fairly simple when it comes to earthquakes, simple earthquake models. And we'll do downsampling, so we'll take our interferogram, we'll turn it into a smaller data set that is still captures most of the information of the interferogram, and then we'll show you how you project models into line of sight and how we run an inverse model. So that's for today, and the homeworks for today will be related to those two exercises. One will be process a different interferogram all on your own without help, and the other will be run a model all on your own without help of a different earthquake. And I see no more questions, so perhaps this is a time for Melissa to start a little timer and let everyone go and get a drink or use the bathroom or have dinner or tea or lunch or whatever. You ready, Melissa?
Yes.
How many minutes? 5, 10?
We'll come back at 11, so say 9 minutes.
Okay.
See you in a bit.
So while we're waiting for Eric to be ready, make sure your OpenSAR lab, Open Science Lab instances are up so you can follow along with the notebook that Eric is going to show. Oh, what happened to yesterday's music?
Was there music?
We got beeps today. Eric, the floor is yours.
Let's It's not showing my video. What's going on? Okay, there it goes. Zoom is being
not as fast as it sounds.
no, maybe yes, it's not zooming along. Okay, so I think probably people know already. I'm a geophysicist at the Jet Propulsion Laboratory, and I'm going to be talking today about processing Sentinel-1 TOPS mode data. And we'll be using a notebook that's in the archive as module 2.1. Maybe I should share not the whole screen, but just this notebook. Let me see if I can do that. This is it. Okay. Does that look good?
Looks great.
Oh, great.
You might
So,
want to zoom in a little. I don't know. It might be easy to
sure.
read.
Does that look better?
Yeah.
Okay. TOPS mode is a very special mode. So we have a special app in ISCE2. It's called TOPS app. And this will work only for TOPS mode data. And it really only works for TOPS mode data from Sentinel-1. The Argentine SAOCOM satellite also uses TOPS mode, but they they don't actually operate it in a mode that's compatible with doing InSAR interferometry. So even though they actually acquire some TOPS mode data, you can't use that with ICE2 processing. One of the things to remember is that there's a new version of ICE that was released a few months ago. It's called version 2.6.4. If you get Sentinel-1C data, you're going to need to get this new version. If you had an older version, it won't support Sentinel-1C. Sentinel-1C satellite was launched in December and finished commissioning in the end of March or early April of 2025. Because they've designed these satellites, A, B, and C, to be fully compatible, you can combine any combination of A, B, and C into interferograms. So that's a big advantage of the way they've designed their constellation and the way they maintain the orbits to be all interferometrically compatible. Later this year, they are going to be launching Sentinel-1D, and then sometime after that, they're going to be decommissioning Sentinel-1A, which has been in space now for over 11 years. So we're going to use a Sentinel-1 data set here in this tutorial that's a pair of scenes that covers an earthquake that happened in 2020 in Nevada in the area called the Monte Cristo Range. And that's what the data set we're going to use. So at the beginning of this notebook, we have to import the various things. Notice it actually says version 2.6.3. There's a configuration problem when they uploaded version 2.6.4. They forgot to update this version number. So even though I have version 2.6.4, it's reporting 2.6.3. That's just a little oversight in the person that set up the release. So the first thing we do is we set up the directories. We're going to do the processing. There's a directory for the data, SLC. It's under, first we have set up a data directory, and then under that an SLC directory. SLC is the single look complex image. That's the lowest. It's called a level 1 product. It's the radar image already focused into, but it hasn't had any looks taken to it. And it's in complex radar pixels.
Eric, Eric,
So
before we get too far, there are some people who are reporting problems with the kernel. Maybe you want to show which kernel to use.
yes, right. So one of the key things here is you have to go and select the kernel. You want to have the kernel set to Python Earthscope InSAR. I did some of this work earlier with a local kernel, this local Earthscope InSAR. So it might be that your notebook is set to looking for the local Earthscope InSAR, but you won't have that in your virtual machine unless you build it with the optional build step. So you need to select this Python kernel, a Python Earthscope InSAR. That should be pre-built in all of your machines. Anything else?
There's one more question, but Gareth is answering it, so you can go on.
Okay, so we also need the orbits. The Sentinel-1 data does not include a high accuracy orbit with the data, so we have to download the orbits. So we set up an orbit directory, and then we also set up a directory called InSAR, where we're actually going to do the InSAR processing. So to save time here, we've pre-collected all this data so that you don't have to download it. It's in this S3 bucket. S3 is a simple storage system that's part of the Amazon cloud system. And with this command, you can download the data. Did I skip something? Let me restart kernel. Yeah, if you change the kernel, you have to go back to the beginning and start running the steps again. And I didn't do that. So this is actually extremely fast to download because it's coming from one part of the Amazon cloud to another into your Amazon cloud virtual machine. So this is very fast. And it has all the data in it. And then at the end, it just copies it into those directories. So once you've downloaded it, it's actually we can actually look at the data. So now I'm going to describe the some of the characteristics of TOPS. As Gareth mentioned earlier, TOPS is called it stands for Terrain Observation for Progressive, but with Progressive Scans. It's kind of a weird acronym. It's actually it's actually what we call a backronym, where we had the TOPS initials, and then they created an acronym to fit those initials because it was originally created as the opposite of spotlight mode. So they took the spotlight mode and they reversed the word spot into TOPS, and then they created this acronym out of TOPS to make. That's why it's kind of a weird name, but it as the satellite goes along, it actually rotates or scans the radar beam. So there's 3 different subswaths in the Sentinel-1 TOPS mode, and during a burst, so it sends out a burst of pulses to on one subswath, and the first pulse is sort of looking backwards, and then in the middle of the set of pulses and the burst, it's looking straight to the side, and then at the end of the burst, it's looking forwards. And by doing this, they get a more even amplitude image. And then once they're finished with that burst, then they start a new burst, a new set of bursts for the second subswath that's shown along here. Again, it starts by looking backwards and then ends by looking forwards. And then after that burst is done, it starts on another burst in the third subswath. So it does a burst of pulses in one subswath, then it switches to the other subswath. So the fundamental unit of Sentinel-1 data is one of these bursts of one subswath. So in fact, the ASF has now offered a service where you can actually download and process a single burst. And if you only want to cover a small area, the bursts are about 70 kilometers wide and 20 kilometers along track, as shown in this figure here. Each one of these bursts is one full subswath wide. It's about 75 kilometers, and it's 20 kilometers along track. And then there's the three different subswaths. So if you look at the raw data, you'll actually see that there's a bunch of individual bursts. As part of the processing, after we do the interferometry, then we can combine the bursts and put them together into one big scene. This is a lot of complexity, but that's the way they decided to build this radar, so we have to deal with it. The ISCE system has a different type of complexity, but after it's processed to the single look complex image, you won't see any of that. You'll get a single look complex image that looks basically like a continuous image. I don't want to get into the details of how ISAR does its acquisitions because that would take another hour. Okay, so as I mentioned, the first thing we get is SLCs. These steps here will download using the ASF search function. This is a applications program interface for downloading directly from your Python or Jupyter notebook. In this case, it reads from the netrc file that you should have in your system, but you need to enter your username and password. Because I've already downloaded these data from the S3 bucket, it says, well, we already have that data. We're going to skip the download. So that step, but if you want to process a different scene, it won't be available from the S3 bucket. And then you need to find these scenes and put them in here for download. And we can see that there's the Sentinel-1 data is stored in this zip file. There's actually a number of different pieces to the Sentinel-1 data set, and they're all zipped together into an archive that contains all the files. And ICE2 TOPS app knows how to get the data out of the zip file, so you don't need to unzip it. You can save some space if you by not unzipping it. As it explains here, you can, if you do unzip it, then the zip extension gets changed to .safe. That's the details of the file format that they use. So then, in addition to the safe file or the zip file, you also need the orbit files and these auxiliary files. They changed how you can download the orbit files. We used to have this program called Fetch Orbit. It only works now if you have because they changed to this new Copernicus data system, data space ecosystem, you have to go and get an account there and set up an API key and password. So unless you do that, then this step won't work. It'll just fail to find the orbits. So we're going to use this other utility. It's called Sentinel EOF. The orbit files are EOF files. And this program was written by Scott Stanowitz, who's one of our instructors here, a JPL radar engineer. And it goes and grabs the Sentinel orbit files, EOF files from a archive, a copy that the ASF keeps. So that's, and if you don't have that pre-installed in your kernel, then you can run this pip install and then download the orbits this way. In this case, the orbit files were actually included in that file that we downloaded from the S3 bucket, so it found that the file already existed, so it didn't have to do the download. So now we finally have all the data. The instrument calibration files used to be important when they first launched Sentinel-1. They had they had to take some time to get all the calibration parameters right, and they provided different instrument files for different date ranges. And in general, you don't need to worry about this unless you're using data from very early in 2015 when they had just first started operating Sentinel-1A. So we're just going to skip over that at this time because it's not relevant unless you're interested in 2015. So the next thing we need to do is set up the configuration file for running the ICE2 TOPS app program. ICE2 uses a file format. It's a type of text file that has a specific type of format called XML. You may have heard of this in some other context. This is the format of XML that ICE uses. ICE2 uses. ICE3 does not use XML. That's going to be something we have to change in the future. So this particular function is being set up to write out the XML file for TOPS app. And with these parameters to set up the area, you need, if you want to specify a specific area of interest and not process the whole scene, we want to process just subswath all 3, because we don't need the whole scene. We're looking at quite a relatively small earthquake. It's not going to take up the whole 250 kilometer wide swath. This is the number of looks or pixels average in the range direction, 7. Number of pixels average in the azimuth direction is 3. We want to do the phase unwrapping, and we also want to do dense offsets. So with SAR data, we can also do this pixel offset tracking or dense offsets to be able to measure displacements when they're very large. So that's one of the XML files that specifies the interferogram properties. Then you also need an XML file that has the information about the reference scene. This is the first scene that we're going to have in the interferogram, and the secondary scene. So to do interferometry, we have to co-register the secondary scene to match the reference scene. And that's what all this code does, is set up those files. You can then, once we can take a quick look here and see it's created these. I've already run all the processing, so there's a bunch of other files here, but this is the topsapp.xml file that I was just discussing. The syntax is highlighted here in the Jupyter Lab interface. These ones in cyan are comments and not actually being used. That's the interferogram configuration. And so then there's also the reference XML that specifies the reference scene. It's in the SLCs directory, and we're just telling it to look at the zip file. And we also have to tell it the directory where the orbit is stored. So that's for the reference scene. We're using the 2020-511. That's May 11th of 2020 as the reference. And the secondary scene is 6 days later. It's from 2020, May 17th. You'll notice that this is Sentinel-1B. The reference is Sentinel-1A, and that's why they're only 6 days apart. Each given satellite only repeats every 12 days, but by having the two satellites, the Sentinel-1 constellation reduces the time interval to 6 days. Sentinel-1B stopped working in December of 2021, and Sentinel-1C, as I mentioned earlier, only started operations in March of 2025. So there was about a 3.5 year gap when there was only Sentinel-1A, and they were back to having only 12-day repeats. Now they're back to having two satellites, Sentinel-1A and Sentinel-1C, and they expect to maintain that later this year by getting Sentinel-1D in the same orbit and working with Sentinel-1C, because then at some point they're going to turn off Sentinel-1A as it's getting old and not working as well as it should. And it's getting low on fuel. So that's all the data we have. Those are the files we need to run TopSap. This is the command to get help from TopSap, topsap-help, and you can get all this. These are all the different parameters you can set in TopSap, and there's additional information on these in the in the ISCE2 directory. But generally, the key things that you want to use are the input file. If you don't specify the input file, it just looks for topsap.xml. The main topsap.xml file then tells which reference and secondary scene files to use. And the other thing to use is this -- steps. When you add this -- steps parameter to your TopSap run, then it saves the information at the end of each step of the processing. And then that allows you to go back and rerun the processing from that step forward, because it's saved the full amount of information it needs to restart the processing at a given step. Okay.
Eric, at this point, I guess you're going to show the TopSap XML file. Are you going to open it in the file browser to show that you can do that?
Yeah, this is the TopSap XML file here.
You could actually edit it here if you.
Yeah, you can edit it here if you want to change something. Change this to 65 instead of 68, or I don't know. I'm not going to change it permanently. We could change the number of looks if we think we need to take more looks because the coherence is low and we want to average more to reduce the noise. We could decide we want to do more than just swath number 3. And up here is where we're telling it that the reference scene information is another XML file called reference.xml, as I just showed you, and the other file, secondary scene, is in secondary.xml.
Someone did
Give these
ask.
different names.
Someone did ask about the setting the number of looks in the Q&A. And generally speaking, my response was, generally speaking, the defaults are good. Give you approximately square pixels and so on, but maybe you could elaborate a little more on why those numbers are.
Does it explain in here? It has something in here.
Oh yeah.
Yeah, we're specifying the looks to be 7 and 3. That's because the spacing of the Sentinel-1 TOPS mode is much finer in range. It's roughly 5 meters in the range direction. The spacing in the azimuth direction is roughly 15 meters. So that's why we want to have a ratio of roughly 3 between the, we want to take more looks in range and fewer looks in azimuth to get the pixels to be roughly square. In this, we also specify the region of interest. That's optional. You don't need to do that. But because we're only looking at a specific area to get this earthquake, we specify that saves time to process just a subsection of the scene. And we're not specifying a DEM. You can specify a DEM here by uncommenting these files that are these lines where there's this pattern here, open less than exclamation point dash dash. That's the beginning of a comment. If we remove that, then it's no longer a comment line. And then there, at the end of the comment, there's a dash dash greater than symbol. So by deleting that open comment and end comment, then this line would no longer be commented. But I'm going to leave it commented out in this case. If we have the DEM commented out, then TopSAP will go out to the NASA server for Shuttle Radar Topography Mission, SRTM, and download a DEM. But you can also provide your own DEM if it's in the right format. One key point is that the DEM needs to be converted to ellipsoid heights. All the radar processing is done relative to an ellipsoid, a smooth elliptical approximation of the Earth, not the geoid that actually, or sea level that most DEMs are used, are referenced to. So in fact, the SRTM data is referenced to a geoid called EGM 96, but the downloading process automatically will do the conversion to take that geoid heights and convert them to WGS84 ellipsoid heights. It's also possible to specify a different DEM for geocoding. That's why there's this second line here, geocode DEM. In general, because the first part of the processing is done at the full resolution before taking any looks, you want to have a high resolution DEM as possible for the first for the main DEM that's used in the processing sorry, double clicked. That should be high resolution. For in this case, it's SRTM 1 arc second or 30-meter spacing. But then after you take looks, maybe after taking 7 looks and 3 range looks, it's closer to 50 meters. You might want to use a coarser DEM for geocoding, just to produce a smaller output file. That's why there's an option here. And that would be useful if you're taking more looks, which is what we do in places where there's a lot of vegetation, for instance. And then it also explains here about the reference and secondary .xml file, as I explained. So because this was set up as a function back there, it's actually this line here that writes out those files. Because I've already done the processing, there's a bunch of other files here. But if you are just starting your processing, you should just see the reference.xml, secondary XML, and topsap.xml file at this point. Okay. So this is just telling about if you want to find out what steps, because we can actually tell TopSap to only do a certain step. That's the function we're going to be using here to not just run through the whole process as a black box, but to go through the individual steps. This shows you all the steps in the standard Sentinel-1 processing. You have to do the steps in order. You can't do step number unwrap until you've done all these previous steps. So if you've done all the steps, then you can go back and restart from one of these steps, but you can't do a later step without having completed all the steps before it. So finally, you can start the processing here. This command just moves the, does basically a CD like you would in a Unix terminal. Change directory. And the first step is just to do what they call startup. And it just checks to make sure that all your input files are available. And that doesn't do anything more than that. That means after you run that, then because we've ran this with the step command, it saved it here under the pickle directory. There's a pickle. All these files are the information that's saved after doing the step, and we have a startup file and a startup.xml that contains all the information from that step. And because I've run all the steps, I have pickle files from all the steps here. Okay, so the next step is to actually do the pre-processing. So in this case, it has to extract the subswaths from the different and the bursts. In this case, we specified an area that's relatively small. The full scene has about 9 bursts, usually 9, sometimes it's 10. And it found that it needed 4 of those bursts to cover the area of interest that we specified. And it then put that information into the data files and set it up for the next steps. So it did that for both the reference scene and the secondary scene. And then we can look at the files that it created. So in fact, to be more efficient, the TopSap sets up a virtual reference to each burst to the SLC data. It doesn't actually make a copy of the SLC. And it also creates this XML file that tells ICE exactly what this burst has. As we can see, we're using data from the interferometric wide swath beam 3. So it's under this IW3 directory, and we extracted 4 bursts. You can look at these files if you want with Vim or with the editor here. This is all the information that ICE needs to know about what's in that burst. So the next thing is to calculate the baselines between the 2 orbits. And you can look at the file called baselines.log here and see that the baseline between the 2 orbits, this is how far the 2 orbits are apart, has 2 components. There's the baseline that's parallel to the look direction, which doesn't actually have any effect on the interferogram, and the perpendicular component, that's the baseline between the 2 orbits that's perpendicular to the look direction. That affects how sensitive it is to topography. This is 20 meters, so that means it's very insensitive to topography. The Sentinel-1 orbits are generally keeping these baselines very short. Since sometime in the last year, Sentinel-1A has been allowed to drift to some extent, so the baselines are getting longer as that satellite is moving more. But this is old data from 2020 when Sentinel-1A was still in full high accuracy orbits. And so it also matches up the bursts from the reference scene and the secondary scene. So the next thing, it checks to see the DEM. In this case, I've already downloaded the DEM, so it didn't go out and download it. The DEM download depends on the ICE app is set up. TOPS app is set up to download from the NASA Earth Data System, so you need that NetRC for the Earth data login. In this case, we already gave a DEM, so it's already here. But this is a problem where people sometimes get stuck. So we staged the DEM and didn't have to do this step. So the next step is to actually use the DEM to calculate where the radar pixels are relative to the satellite. So we use the DEM and the satellite orbit. Then we know all the geometry of where each pixel in the scene is located in 3D space. So this calculation, this step in the processing actually goes through for each pixel in the radar image and calculates the whole geometry of where in 3D space that pixel was reflected from. And this takes a little bit of time if you're doing a big scene. This is one of the steps that can use a GPU if you have a GPU on your computer. These these machines for our course don't have GPUs, so that's not an option.
And you have to recompile the software, right? With
Right,
keyboard
yeah,
and
you
all
have
sorts
to
of stuff.
compile ICE with the GPU option enabled. And that takes a little while to run. So I set up so you can just run all this in your 2025 ICE Plus directory. I set up a separate test directory and then copied all the notebook and other files there so I could keep things separated. So this is the directory where I'm doing the processing. It's doing the geometry calculation here. So you can see it's done the geometry for the first burst. It has to calculate the height, the latitude and longitude for that burst and the radar line of sight. Then it has to do that for all the other 4 bursts. So this particular step takes some amount of time, up to 20 minutes to run. In this case, it's finished burst number 2. Are there any questions? I haven't been watching the question and answer.
There have been lots of questions. I've been trying to answer them.
Ah,
um, I don't know if anyone wants to speak up and ask their own question out loud. If there's anything that,
Sorry, can I ask a question?
of course.
Okay, thank you, Eric, for the introduction to this tool. Actually, I think some people are also struggling with time series analysis. Does this Top Apps Pi supports the time series analysis for example, you have a 5-year actually interval of satellite imageries that you want to co-register them and then unwrap them to just feed them to MintPy for space analysis. Does it also support that or not?
no, so TopSap is designed to process a single pair of scenes to make one interferogram. There's another system. It's an actual whole workflow you need to set up. It's called TopStack, and that's for doing the stack processing, where you want to take a whole stack, up to 5 or 10 years of Sentinel data and co-register all the scenes and then form interferograms. That's kind of a more complicated process that we're not going to cover in this course in any detail, but it is available. Certainly, what you want to do before you start the stack processing is run Top's app and figure out you know the area of interest you want to cover, the bursts, the beams, the number of looks, and things like that before you just launch. Because if you were to do stack processing in some places, like here in California, we have over 300 acquisitions of Sentinel-1 data over Los Angeles. So if you want to do a stack processing on that, you're going to spend like a week of processing. So one of the things you definitely want to do first is run TopSap and make sure that you have all those parameters set up correctly. Okay, so the topo step is finished in my run, and we can see that it created the height map for each burst, the latitude map for each burst, the longitude map for each burst, and the line of sight vector for each burst. And these are in radar coordinates. That's what this RDR here means. So that's done. You can, these are actually images. You can look at these files. Because they had this VRT file, you can use GDAL on them and get information. We can see this is looking at the line of sight vector for burst number 2. We're only this is just one subswath, and it's showing that the line of sight vector incidence angle from vertical is varying from 41.6 degrees to 46 degrees across this subswath 3. Subswath 3 is the furthest out subswath from the satellite. And then the second band here is the azimuth angle. And the azimuth angle is almost constant, but not quite. Okay, so we can actually look at these files if you want to see what the files look like. Then this next step actually opens one of these files. We use this XRA program and we can see this is the height map for burst number 1. It goes from roughly 1,500 meters to 2,500 meters. So there's about 1,000 meters of topographic relief within this one burst. This burst is 20 kilometers along track and about 80 kilometers wide. You can look at all the bursts if you want. This is the line of sight incidence angle. As I mentioned, it goes from 41.6 to a little over 46 degrees, and it's basically there's just a linear trend across the burst. These are all the bursts and radar coordinates. With the radar coordinates in the ICE definition, the left-hand side of the image is closest to the satellite, and the right hand is farthest away from the satellite, and the top edge of the burst is the earliest in time as the satellite's going along, and the bottom edge is the later in time. And depending on whether the satellite is going north or south, or and looking east or west, the bursts can be are going to be flipped relative to what you're used to. So we can also use this other custom plot function here that's a different way to do these same plots. These XRA plots are a faster way to do the plotting that was added by Scott Henderson back in 2023. As you can see, there's a lot of people who worked on this notebook over the years. So it's had a lot of people working on it. Where are we? Okay, so the next thing is to calculate something called enhanced spectral diversity. So as Gareth mentioned briefly before, the fact that the TOPS mode is doing this along track scanning means that we need to have the two images co-registered in the azimuth direction to a very small fraction, basically within 1,000th of a pixel. If we don't have them co-registered that accurately, then we're going to get some residual phase ramps that are caused by that scanning action. So the orbits are generally very good for highly accurate for Sentinel-1, and you can co-register based on the orbits. But in fact, there are some azimuth offsets that are caused by the ionosphere. And this ESD, or enhanced spectral diversity step, will do this calculation to estimate what the optimal offset is between the reference scene and the secondary scene to get the best coherence and avoid those phase ramps. And that will tend to correct for the ionosphere to some extent. There is also an ionosphere correction that's been added to TOPS app. We're not going to have time to talk about that today.
We're running up to the time of a break.
Yeah, so maybe I should go back into this enhanced spectral diversity after the break.
Yeah, we'll give some people some time to catch up, maybe with their processing up to here.
Yeah, so this custom plots function is in the tutorial home directory. If you copy your notebook to a different directory, you also need to copy the this custom plots.py file. And you need to make sure that if you, this was something that I just changed this morning. I added, you need to update your version of the notebook. This custom plots notebook needs to be in your home tutorial home directory, wherever you're running the tutorial. But this line was a line that I added just this morning. So if you kept your machine running since yesterday, you would need to rerun it, shut it down and restart it in order to get this updated version.
Or just type it in.
Yeah, or type it in here to get this. You can do the rest of this tutorial without this custom plots running. So if you want to just keep going, then you can just go to the next step. Okay, so we're going to take a break and for what, 7 minutes?
7 minutes, yeah.
Great.
Are you ready, Melissa, with fun, exciting countdown timers and stuff?
Do we get music?
We'll see.
Yes.
Nice.
Music is back.
Is Eric back?
So at home.
Hi. So I guess people are coming back from the break. I'm back here. People still see my screen?
Yes.
Yep, you still see it.
Great. So we started the processing of the enhanced spectral diversity. As you remember, as I covered earlier, you may not remember, this TOPS mode has this scanning. So that means that at the end of one burst, it's looking forward. At the beginning of the next burst, it's looking backwards. And that means they're actually looking at the same point in there is a little bit of overlap between the bursts. And that means that burst is imaged with two different look directions. They're actually separated by about 1 degree. And that means that we can use this spectral or a long track azimuth spectrum diversity to look at this overlap region and estimate what's the amount of offset between the two, the reference scene and the secondary scene. So this is showing it in the Fourier transform space. I'm not a real radar engineer, so I can't explain this in detail. So the key thing is that the top, it cuts out, we cut out just these overlap regions for each, where one burst, the end of one burst overlaps with the beginning of the next burst. We have 4 bursts in this particular subset, so there's actually 3 overlaps. The burst 1, burst 2 overlap, 2, 3 overlap, and the 3, 4 overlap. So if we look here in the reference overlaps, so it has to do this also for the reference scene and the secondary scene. So if you look in this reference overlaps directory, there's the overlap between the burst 1 and 2, 2 and 3, 3 and 4. And then and then we have to do that for the, it actually separates out that overlap region for the burst that's above and below along track. So that's why there's these top and bottom files. So you can actually look at these scenes. This is the top, the burst overlap subsets. This is the burst 2 for the overlap region. This is burst 1 for the overlap region. You can see they look highly similar. We can make an if you look at the raw phase of that burst overlap, it looks random. And that's, I think, what Ann discussed yesterday, that a given SLC has random phase. It's only when we take the interferometric difference between the phases that we can then see the interferometry. So I've already run all these steps here, so I can just scroll down. So the first registration of the secondary scene to the primary scene is done by this step called coarse offsets. That coarse offset is just doing the estimate of the overlap of the relative location using the orbit data, and it goes through and does all that, and it then makes the interferogram. This is the amount of azimuth offset that's estimated from the orbits. You can also see the range offset from the orbits, and it varies only a few pixels. No, a few thousandths of a pixel across the image. So we need to then resample the secondary scene to make it in co-registration with the reference scene. That's what this next step does. It uses that coarse offset information to resample the secondary scene so that it's in precise co-registration with the reference scene. So then this next step actually combines the offsets into an interferogram, and there's 3 different offsets for between the bursts. So there's an interferogram for the 1-2 offset, interferogram for the 2-3 offset, and interferogram for the 3-4 offset. We can see what the interferogram looks like. You can probably guess now that most of the that the earthquake is in this offset field of the between burst 2 and 3. That's why there's a bunch of fringes in this particular offset. Burst overlap. Oh, that's a question I wasn't supposed to answer that. Sorry. Okay, so now that we have this interferogram for the this is the interferogram using just the top, the earlier part of the bursts. Then we can also make an interferogram for the second or bottom part of the bursts, and then we do a double difference interferogram, which is subtracting the top interferogram from the bottom interferogram, and that is then done in this prep ESD step, and it then calculates what's the differential offset. This is the coherence of that combined double difference interferogram. You can see there's some areas of low coherence. This is partly due to the earthquake deformation. Other places it's due to steep topography. And then this is the differential phase. And again, there's a little bit of an effect of the earthquake here in the middle, but in general, this is all pretty close to the same phase, which is what we expect because this is mostly this is proportional to the misregistration of the two scenes. And with the next step here, we actually take a histogram, and we can see that the azimuth shift for different pixels here, calculated from that phase of the differential interferogram, goes from minus 5/1000th of a pixel to plus 5/1000th of a pixel, with an average that's a little bit less than 0. So that's the amount of misregistration that we need to account for to get the most precise co-registration. It also calculates the misregistration in the range direction. That's just done from pixel offset cross correlation. It's much less precise because we're just doing it with amplitude cross correlation and not done with the phase. But we also calculate that, and that's the range misregistration. So now that we have calculated what the average azimuth or along track misregistration is and the range misregistration, we can then do the resampling using these fine offsets or revised offsets. So that's what this next step does. TopZap with fine offsets and calculate the fine offsets and then do the resampling. You can see after that, it's done the fine offset calculation for each pixel. Then it applied that with the fine resampling step of the processing. And this, as I mentioned earlier, we're actually going to skip this ionospheric estimation. This is an optional thing that was added later, and it's one of these parameters that's optional in the topzap.xml file. You set this do ionospheric correction to true and do apply. So first is to calculate the ionospheric correction, and the second is to apply it. And it's a bad idea to do both the enhanced spectral diversity and the ionospheric correction because they're really doing almost the same thing in most cases. So if you do the ionospheric correction, you should turn off the ESD estimation. So then you would skip all those ESD steps and do the ionospheric correction. The ionospheric correction is doing a split spectrum in the range direction. This is the same kind of correction we do with L-band data. Oh, that's spelled wrong. Sorry about that. It's just a text part. Anyway, doesn't matter. This is the same thing we're going to be doing. It's automatically done in ISAR processing. It does estimates this ionospheric correction for you using either the range spectrum, or because we have the second band, the range spectrum is already split, and therefore we can calculate the ionospheric estimate from the two bands. This step is part of the steps in TopSap, but since our XML file didn't specify to do that, it doesn't actually do anything. So the next step is that now we've done these precise co-registration between the two. Move the secondary scene to be in precise co-registration with the primary scene. We can do the interferogram for all the full burst, not just the overlap. So this is the interferogram for the full burst. We've taken its burst number 3. This is the burst that has most of the earthquake in it. It's again 20 kilometers a long track and 80 kilometers wide. That manages to catch most of the earthquake deformation here. And you can look at the other burst too here if you want to change the burst number and see the other bursts. But then as I mentioned earlier, we can, after we've done all the interferogram processing, then we can finally merge the bursts together and make a large interferogram. So this next step, merge bursts, then merges those 4 bursts. We were only using 4 bursts here, but and puts them together into one combined or merged interferogram. So that then goes in this merge directory. All this other calculations were done in the InSAR fine interferogram and directory. That's where the interferogram is with the fine offsets. Coarse interferogram directories with the coarse offsets. And the final merged interferogram is in this merged directory. So a lot of different steps, but that's what we have to do to deal with this TOPS mode that has these bursts and spectral, this scanning mode. Fortunately, with NISAR, we're not going to have to deal with all this. It's just going to be, after the SLC is focused, it's just going to act like it's just all one big strip of data. And there's other satellites that are operated in what we call strip map mode. We used to include strip map mode processing as one of the lectures, but we moved that to the supplemental information this year. So if you go to ICE Plus, it's down here under supplemental notebooks number 3. So that's here if you want to see how to process strip map data. And that would apply to ALOS 2, ERS-1, ERS-2, NVSAT, a lot of other satellites, Cosmos, SkyMed, TerraSAR-X, maybe ISCE if you get data that has a interferometric baseline. So then once we have our merged interferogram, the next step is to filter it. We apply a filter that's called this filtering step, it uses a power spectrum filter. It's not really explained here. I think it's explained in that strip map app notebook we used to that's in the supplement. But it's a special type of filter that is nonlinear, and it tries to keep the detail in places where there's a high fringe rate, like where close to where the earthquake is, but also do more smoothing in the smoother areas. So we can see in this case, we're in Nevada. There's very little vegetation, almost zero vegetation. The filtering doesn't do a lot, but it does make the phase a little bit smoother, and that makes it easier to do phase unwrapping. We use Snafu. That's the Stanford phase unwrapping program. It was written by Curtis Chen when he was a student at Stanford. Curtis now works here at JPL, but he still maintains Snafu as a Stanford piece of software. It's already built into ISCE, so we just that's the default unwrapping algorithm in ISCE, and the other option is this option called ICU, which is a different unwrapper that we originally wrote for doing the SRTM data processing. I really don't have time to explain what that does. But this is the unwrapped phase from the somebody asked, does ICE2 support processing of SAOCOM data? Yes, you can process the SAOCOM strip map data, but not the SAOCOM TOPS mode data. Their wide swath TOPS mode data is not, the bursts are not lined up in the way they acquire the data, and it's not possible to make interferograms out of it, but the SAOCOM strip map data can be processed with the strip map processor. So the unwrapped phase is much easier to interpret. We can see where there's an area of negative phase here. That means that the satellite, the ground moved towards the satellite. Over here, yeah, what's the sign convention here? That's something you always have to check. I use the reference scene. Let's go back here. The reference scene is the before scene, and the secondary scene is the after scene. So that means that if the ground surface is further away from the satellite on the second scene, then it has a positive phase here, and the negative phase means it moved towards the satellite. The distance between the ground and the satellite decreased. There's another file that's called the connected components. The SNAFU program goes through it and it looks at the coherence file that's calculated, and it and how the phase is continuous in between points, and it determines whether there's whether that unwrapped phase component is connected. You can see there's some little dots here that are unconnected. Those are in places where it's very noisy and there's a lot of deformation. So that's, if you see these unconnected components here, that's an indication that probably the phase unwrapping is not so accurate in that area. So that's in other cases, the connecting component will be set to 0, and that's a place where snafu is estimated that the unwrapped phase is not reliable at all, and you shouldn't really use it. So this connected components file is a key piece of information that comes out of the snafu unwrapper. There is an option to do two-stage unwrapping. This is this is this is if you have a scene that has some patches that are not connected, and you want to try to what this two-stage unwrapper will actually try to estimate what's the relative phase between the different connected components and then adjust them. In this case, basically the whole scene is in one connected component with only these tiny patches, a few pixels that are on different things. So we're not actually don't need to do the two-stage unwrapping, and it's not done unless you set this property to be true. Finally, now that we've done all this work of unwrapping, this scene is still in radar coordinates. This left edge is the part of the scene that's closest to the satellite, and this top edge is the part of the scene that's earlier in time as the satellite's moving along the orbit. But once we geocode it, we can see that it's now flipped in the east-west direction because the satellite is on the descending track. The side of the image that's closest to the satellite is on the east side. So this is now in regular geocoded coordinates, and you can use this for your modeling of earthquakes, as Gareth is going to discuss later. You can actually redo the calculation with a coarser DEM. This explains how to downsample your DEM. You might want to re-geocode it with a coarser DEM because you don't need all the details. This is the geocoded at 120 meter pixels instead of the 30 meter pixels that we got from the using the full resolution SRTM DEM. For modeling purposes, you generally want to have not so many pixels, so it's often an advantage to redo the geocoding with a coarser DEM. It's also possible to put in your own DEM and there's some explanation here of how you would do that. So there's also dense offsets. That's built into the TOPSAP processor, and that is a way to do cross correlation of the amplitude images. What TOPSAP does is it completely resamples the whole secondary image and merges the bursts together and to make an amplitude image that's the whole scene without the burst boundaries. It does the same thing for the reference scene. Then it does the cross correlation and estimates the pixel offsets and then puts them into this dense offsets.bil file. And this can take quite a while to run. Just skip past that. And look at the offsets. So as I mentioned earlier, the range pixel size is around 5 meters on the ground. It's actually 2.5 meters in the slant range. along range direction. So we have a pretty good resolution of the azimuth of the range direction pixel offsets. And we can see the same pattern. So this is still in radar coordinates as like the interferogram, and it shows the same pattern. There's a negative displacement closer to the radar on the and a positive displacement further away from the satellite in radar coordinates. The azimuth offsets, because the pixel size is very large, is around 14 meters for the Sentinel-1 data. We can't really measure the pixel offsets to better than about 1/10 of a pixel. So only if the earthquake motion was over a meter would we see a significant signal. And this is a relatively small earthquake, and we don't see a clear pattern in the azimuth offsets. And then you can also geocode these. And that's actually done by in the processing if that's enabled. So this is the geocoded range offsets. It has the same pattern as the interferogram, and it should be about the same magnitude, but it's much noisier. We can't, it's on the order of 1/10 of a pixel. In this case, it's 1/10 of 2.5 meters, so we can only measure within about 25 centimeters the range offsets, and we can only measure the azimuth offsets within about a meter or meter and a half. It's good for very large earthquakes like magnitude 7, 7.5, but it's not so effective for this magnitude 6 earthquake. So that's the whole sequence of Sentinel-1 processing. I think there's time here to talk about some of the other things. So what can we do with these files after they're created? So let's go here. You can create a terminal here, trade terminal. And this terminal, because I opened it while I was in this directory with all where I did the processing, we can see our InSAR directory. We can go to the merge directory. This is all the merged interferograms. The final interferogram is filtered topo phase. The topo phase means that the topographic phase has been subtracted, unwrapped, and geocoded. So this file right here is the filtered topographic phase removed, unwrapped interferogram that's been geocoded. And there's an ISCE function called ISCE to GIS. I have to, because I opened this terminal, I'm not in the EarthScope InSAR environment, so I have to activate it first. EarthScope. InSAR. Okay, now we should have access to the ICE programs, ICE to GIS.py. I want to convert this filth to topo phase. And you have to specify the format. So in this case, I'm going to make a VRT file that we can then use with GDOL. Oh, we have to put the VRT first, sorry. Oh, I have to put a dash I. Oh, yeah, there's something, it's kind of weird about the way that ICE works. Um, the files that ICE works with, it saves all the information about the files in XML file. So there's a filter .unwrap.geo.xml file, and this file is written with the path to the directory, to the file, and then you can see that the file name here actually says merged. So because I'm in the merged directory, when it tries to read the file, it doesn't find it. So I actually have to go back up to the InSAR directory and run this ICE2. This is an annoyance that's in ICE2 because the way that path name is embedded in the XML file.
There is a script, right, that allows you to correct for that if you copy it.
Yeah, you can correct for that. It's another thing you can do.
Fix ICE XML or something like that.
So we can also use this other command called ICE. So that creates the VRT file. Once we have the VRT file, we can use GDOL info on the that would allow you to load this file directly into QGIS or something like that. This is still in radar phase, so it's in radians. If you want to do modeling, you're going to need to convert it to meters by combining it. So you could use the GDOL command to convert it to a GeoTIFF, or you can just load this using that VRT file. You can just load this directly into QGIS or other software that knows about how to read that virtual data file. You can also use this ICE to GeoTIFF function. And that will make a GeoTIFF directly. You specify the input file and the output file. The unwrapped phase has two bands because it has the unwrapped phase as one band and the as we can see here from the GDOL, there's a band here. Band 1 is the amplitude, the radar amplitude image, and band 2 is the unwrapped phase. So if you want the unwrapped phase, then you want band 2. If you want the amplitude image, you want band 1. How much time do we have left in this session?
13 minutes.
So maybe I can show how we can load this into QGIS. I need to share my screen rather than just that one window. Okay, that's A new empty project. We go over here, find the file. I want to do unload it as a raster. And oh, wait a minute. Right. Of course, I can't load it into QGIS until I've downloaded it to my computer. So first thing you want to do if you want to work with this file is download it. So if I go to the merge directory here, and we find this filtopophase.geo, I go up here, I right click on this, I do download, right click on the VRT file, download that. The XML file also might be useful. So now in QGIS, when I download that, it's in my downloads directory on the Mac. I specified the VRT file to open because that's what QGIS knows about. QGIS knows about only about VRT files, GDOL. And we can see now that it has two bands. Band one for the default is to make this funny color image. It's the amplitude image and the unwrapped phase. So I'm just gonna first make an image of the band one. That's the amplitude image. It's very dark. This is one of the characteristics of radar images, that they have a huge dynamic range, and there's some pixels here that are very steep slopes facing towards the radar that are very, very bright. So we need to adjust the lookup table. I'll just do a 2% cut. Now we can see better the amplitude image. Some of these flat areas in the valleys of the basin and range, the basins are very, very dark. They reflect very little radar. And then the steep slopes and rough alluvial fans are reflecting the radar more. I'm going to make another version of this with the unwrapped phase, band 2. Now we can see the unwrapped phase here. I'd like to have the color scale going the other way. Invert color ramp. So this is ready to do analysis. It's still in radar. It's still in radians. We can see the radians go from -17 radians to +34 radians. We need to multiply by divide by 2 pi and multiply by the radar wavelength to get the displacement in meters, or whatever units you use for the wavelength. Now, so the units are still in radians. We have not done the conversion to meters. You can use the raster calculator in QGIS. We're going to give it a new name. Past out. And we need to take band 1 and multiply by the radar wavelength, which is 0.056 in meters, divided by, doesn't have pi built into it. Okay, I'll just put in 6.28. Okay, so now I have a new file that's in meters. Again, we can set the color scale, pseudo color, invert color map. Now the color scale goes from minus 0.15 meters, 15 centimeters to plus 0.3 meters or 30 centimeters. So there's about 45 centimeters of total displacement from the dark blue here to the bright red. And as you may remember, some of these, if we zoom in here, there's these weird kind of discontinuities. Those are likely to be phase unwrapping errors. That was also showing up in the connected components, that there was some little pixels here that are probably not unwrapped correctly.
There were also complex surface ruptures in that.
Yeah, so these lines over here are probably actual surface ruptures. And so you have to be careful to interpret this carefully. Some of these discontinuities are surface ruptures, but this kind of jagged one is more likely to be a phase unwrapping error. So that's something you need to pay close attention to if you want to try to understand what's going on. We can also do a quick blending here. Blend the amplitude image as multiply. Turn that on. Now you can see the combination of the amplitude image and the unwrapped phase. Probably want to make this amplitude image a little bit brighter. Minimum 200.
We had a question asking about the units of the file, and I was replying, well, it's in radians, but you can use image math to convert from radians to meters.
Yes, you can do this with the image math command. So there's also the image math command in in ISCE. There's the if we go back to ISCE here, there's image math.
Now it's kind of a bit hard to see your screen because you got your whole screen.
Yeah. Is there a filtering method to avoid unwrapping error? Well, that depends on how noisy your interferogram is. If it's really noisy, there may be no way to completely avoid unwrapping errors. In a lot of cases, it actually works better to do less filtering. If we go back, where's the, oh no, that's the wrong server. Where's this one? There's a filter strength. Filter strength is one of the properties you can set. The default, I think, is 0.7. But I found that sometimes decreasing this to 0.1 can actually make the phase unwrapping more accurate. It depends completely. If your area has very good coherence, you actually want to do less filtering because the filtering is likely to mess up the fringes. If you have very bad coherence, then you need a stronger filter because otherwise it's just noise. So this filter strength is one of the things you can change. You can also change the window size if you're using the median filter.
And in some cases, you just can't avoid it. You can filter very heavily, but you may bias your phase, or you filter less and you may have phase and wrapping errors.
Yeah.
Luckily, Hyunjun on Friday will walk you through MinPy, where you then use these interferograms for time series analysis. And MinPy has some routines implemented that can, try to correct some of these phase and wrapping errors using the redundancy of the overall network. Or as Paul Rosen says, with NISAR, there will never be any phase and wrapping errors.
Yeah. Yeah, you can. I'm just playing with the amplitude image to adjust it. So yeah, some of these are probably a phase unwrapping errors. They seem to be cutting across the topography. But some of these other ones are actually likely surface ruptures out here in the basin.
There were a couple of questions in the chat, the Q&A.
Yeah, there's a new program called InSAR Explorer. It works with the time series analysis product. So I think it does work with MinPy output. I haven't tried it yet, but it is once you've done the MinPy processing of a time series, then that's a good way of exploring it in QGIS.
Is that an open source
ICU
thing?
unwrapper it works well in places where you have good coherence. It works in a different way. It finds the low coherence area and masks them out in begin with, and then it unwraps the areas that are good coherence. The snafu program unwraps everything, but then it marks the poor quality unwrapping in the connected components file. Whereas the ICU program won't unwrap the low coherence areas. The big advantage of ICU program is it's optimized to work on very large interferograms because it processes it in sections. So if you have a very large interferogram, it could take a huge amount of memory to unwrap with snafu. If you take a full Sentinel-1 scene and you take only like 3 ranged looks and 1 azimuth look, you probably will need 120 gigabytes of RAM to use snafu to unwrap it. But the ICU unwrapper will be able to unwrap it without a problem because it cuts it up into pieces and then does the unwrapping. Okay, I think
tiling as well to make memory lower.
yes, yeah, ICU uses much less memory too, the way because it's cutting it up into sections. You're welcome. So I guess we're running out of time for this particular session, so maybe we should move on to the break.
That sounds good. We can break for 8 minutes.
Okay.
The timer has already started.
Baru's asks,
because in the next section, I think Gareth is going to ask you to participate. So there will be submissions of model solutions that you can do.
Oh yeah, I need to set that up. See you. Welcome back, everyone. The next thing we have on the menu for you is preparing data for modeling. So if you get to the point where you've run your top stack, your top SAP processing, and you have an interferogram, say you have an interferogram of an earthquake that you want to try to use, then the next step would be to do something with it a little more in depth, some kind of analysis of that interferogram, some kind of modeling. So what I'm going to show in the next hour is some techniques for that. We're going to cover a few different things. Firstly, I think at the start of yesterday's sessions, I mentioned, you know, the things you really need to do to model your code. There are a couple of things. One is you need a code that will produce displacement model, produce outputs that are estimates of displacements of the Earth's surface. Okay, and I mentioned a few of those. There's the CADA, which we're going to look at in a bit more depth in a minute. We looked at MOGI sources yesterday as well. But the other thing you have to do is to project those deformations actually into the satellite line of sight. And also I'm going to show you how you go about doing that. Okay, so that's those are the goals. I'm going to share my screen and get to it. Okay, hopefully that's working and looking nice. So I'm in section 2.2 on the ICE Plus deployment of materials, and I'm going to start with this notebook that's called Line of Sight Displacements and the CADA model. So this makes use of a version of the CADA code that was produced for Python by Ben Thompson. It's very easy to install if you want to install it on your own machine at some point. It's just one command, pip install a CADA wrapper. And some of the routines I have in here are going to make use of that CADA wrapper and run it to produce a map of surface displacements from an earthquake, from a theoretical earthquake, I guess. So you need to run all the dependencies. Hopefully, if you're in the Conda, if you're in this guy here, oh, where did that go? Interesting. Where did my kernel go?
3 dots, yeah. If you zoom
If
into
you
it.
lose it, yeah, this built-in Conda N with Python out front seems to have all the things. And if you're running the wrong kernel, you'll get an error message when you try and run this. I did not. Okay, and so what we're going to do is define a few things. Some of them are probably more intuitive than others. The first set of parameters that this is defining are the elastic strength of the elastic medium. There are 2 constants that define that. If those 2 constants are equal, we call them lambda and mu, or the Lame parameters, then your material has a Poisson ratio of 0.25, which means that it's well, you know, it doesn't matter what that means really. That's a fairly standard elastic material. Let's go with that. And 30 gigapascals is a commonly used value for the strength of that. Okay, so this will just establish those elastic parameters. And then here I have a whole series of parameters that define a fault that moves in an earthquake. So the strike is the angle of the compass bearing, I guess, of the orientation of the fault. So a strike of 1 is like 1 degree, which is almost north-south. Dip is 85 degrees. That means it's almost vertical. Vertical would be 90. It dips to the right. So that means that the dip would be 85 degrees to the east. Rake is a measure of the direction that a fault slips. I think -1 is very close to 0, and 0 is pure left lateral, which means if you looked across the fault, it would move to the left on the other side. Slip is the distance that the fault moves. That's 2 meters. Okay, that's quite a generous movement there, consistent with an earthquake in the kind of the magnitude 6s to 7s range. I'm going to say the fault is 15 kilometers long, 15,000 meters. The width of the fault down dip. So the other dimension of the fault rectangle is 10 kilometers. And the fault has its centroid depth, which means the depth of the center of the fault is 6 kilometers. You can also choose an X and Y coordinate. And I'm putting this in the middle of my box that I will define in a minute. Okay. So these are a load of fault parameters, and this is going to define the Okada fault that we use to calculate displacements. For your information, I have included the links to some of these things. If you click on them now, it will take you away from the notebook, so don't click on them now, but come back later if you're curious. You can find the paper by Okada in 1985. It's a highly cited paper because everyone likes this study, because no one had to do the math themselves to calculate these displacements anymore. Okada did the integrations correctly, and then very importantly, he produced a subroutine in Fortran, which he shared with everybody as part of the paper, so everyone could just plug it into their codes, and everyone was happy. It says Okada was a person, and we also refer to the rectangular elastic dislocation code that he developed as Okada, because that was his name. This is a figure from the webpage, which you can also go to. The National Research Institute for Earth Science and Disaster Resilience in Japan has a whole webpage about the Okada models, and the codes and everything else. And this figure came from there, which just shows that in the way that it's set up, you have to make a load of geometrical corrections to actually use this for your own purposes, which this notebook actually goes and does for you. But let's see, you have to define the dip of the fault. You have to define the displacement in different components. There are three particular directions your surface could move in the direction of the strike, which, as you can see here, is aligned with the x-axis. That's the strike slip component, we would call that. You can have a movement in the direction of the dip, which would be the dip slip component, and you can have a motion in the direction which is perpendicular to that, which would be opening. And opening is something that faults don't do, but dikes and sills do. So you can model certain magmatic processes this way as well. You have to define a reference point on the fault plane, which is shown here, or the dislocation, as they would call it, to give it a more general name. And you have to locate that you have to estimate where that is within the fault plane. So you define all these distances along strike and down dip to place it in the middle of your to place it at a specific location within your fault. And so there's a bunch of things you have to do to use this, because obviously we have defined our fault strike as not being the x-axis, and we have a load of fault observation points that we care about that are not going to be in that reference frame either. So you'll see, I won't go through it, but I had to do a bunch of rotations to make sure the coordinates were right. You have to rotate the fault, and then you have to kind of rotate it back again to put all the observation points in the right places. This is a bit of a pain, so you don't have to worry about it. I have done it. And this is now built into all the routines I'm going to show you later on. Anyway, so it does some calculations. It calculates where the centroid of the fault is in this coordinate system. It calculates the amount of strike slip and dip slip given the rake and the slip that you have defined at the beginning. It makes a rotation matrix to rotate the coordinates into the coordinate system that Okada uses. And then here we define a grid that we're going to compute this Okada model over. We're going to have 101 pixels in X and Y, the X and Y directions, and we're going to have bounds of 25 kilometers either side of your origin, which is at 0, 0. So you will end up with, a 50-kilometer wide box, or 50-kilometer wide square, where you're calculating these displacements. Right. And so if you run this, it will do the calculation. It ingests all the things that you tell it. It calculates the X, Y, and Z displacements of every point that you include in here. And it's going to plot out at the end of this the 3 sets of displacements for the model that we just included. If you remember, this was a fault that was basically north-south and basically slipping as a strike slip fault with pure left lateral motion. And so output here is the x displacements, the y displacements, and the z displacements. The easiest ones to interpret are the y displacements, because these are in the direction. This is the motion in the direction, more or less, of the fault. And you can see, for example, positive displacements would be positive y direction, so north, and negative y displacements would be south. And if you stood on one side of the fault and looked across to the other side of the fault, so if you stood on the east side and looked to the west side would be moving south with respect to you, which is left lateral movement. Similarly, if you stood on this side and looked to the east side would be moving north, which again would be to the left. Okay, so this is correct. It is calculated displacements in the right direction. And you can see also that there are other things that you can see in the displacement pattern. There's a large amount of east-west displacement, even though the fault is moving north-south. That is because you're moving only a small section of the material within your elastic medium is actually moving. The rest of it is kind of having to accommodate the movement around of that piece of that dislocation. And one of the components of motion you will get is especially at the ends of the fault, is some east-west movement. And you can see in the north, the material is all moving eastwards. It all has a positive east displacement. And in the south, it all has a negative east displacement. It's all moving west. Okay, so sometimes there are these unanticipated, but actually legitimate, like, additional motions that this kind of model will correctly estimate. And then the other thing you'll see is that in the vertical component, you have these little vertical motions, and these all correspond to basically the ends of the fault. And that's because if you move this material on the west side of the fault to the south, which you're doing here, you actually end up squeezing the crust right at the end of the tip of the fault. And you'll squeeze it and it'll bulge upwards a little bit. And similarly, at the northern end, because you're pulling it this way, you're actually stretching the crust a little bit and it will flex down a little. So that's also captured by this model. Anyway, this is the displacement pattern in X, Y, and Z. That is not what InSAR is going to see, right? The next problem is that we're going to have is how you convert this into something which would look like an interferogram. So that's the next step. So in general, we define a pointing vector. Oh, that doesn't highlight well. I won't bother highlighting it. But that pointing vector, if you recall from yesterday, is a unit vector that points from the satellite to the ground, or at least in the sign convention I'm going to use, that's what it's going to do. I'm going to have a unit vector that points from the radar to the ground target, and it's defined on the basis of two angles. One is the satellite pointing azimuth, which we call phi here, and the other is the incidence of the radar with the ground, which is the angle I will call theta. So yeah, theta is an incidence angle, and phi is the pointing direction. And you can do the trigonometry and work this out if you want. I think maybe on Thursday you will see a version of this where you get some hints as to how to do this. But anyway, assuming you're willing to take my word for it, this combination of things is going to give you the pointing vector in the range change sign convention. So you can tell that it's range change because the z component, the vertical component, is negative. That means the satellite's pointing down. And you can see also that the vertical component is the only one that does not depend on the pointing azimuth. It's purely on the incidence angle. So you can calculate these vectors by plugging in numbers. I have actually here I have a code cell that will just calculate them for you. Just written out this in functions, and I've given you some possible values here. So theta 39 degrees, that is that is a reasonable value for the center of the middle subswath of Sentinel-1. So it's the middle of the Sentinel-1 scene. And you have a choice of two angles. I always forget which is which. Negative 260 is appropriate for the ascending viewing geometry. So the satellite's flying from south to north and looking to the east, looking down into the east. Or you comment that out and use a phi of -100, which would be the same thing but for descending, which is flying from north to south and looking to the west. So you can run that and you will get some numbers here for the pointing vector components. 0.6 positive. Okay, this is the ascending track. So 0.6 it's looking to the east. Okay, that's good. 0.109 for the north components. That's looking very slightly to the north. And then negative 0.777, which means it's pointing quite steeply to the downwards. So of those three components, the Z component contributes the most, and the north component contributes the least. And you can play around with different values of these angles. So I've given you what the incidence angle ranges are for different subswaths of Sentinel-1, for example. So like depending where you are within the scene, the incidence angle will change quite a lot. The pointing azimuth doesn't change nearly as much. Eric mentioned today that it varies by about 1 degree at burst boundaries. So there is some variation within it. It's not a uniform, it's not pointing uniformly in the same direction everywhere. And that's some of the magic of the TOPS mode of data acquisition. It makes it a lot more complicated. But for most purposes, most of the time, you can, for the purposes of display here, we can more or less ignore that minor variation because it's not going to contribute a whole lot to what we see. Okay, so what we can do now then is multiply those three data sets that we have calculated, or data sets, those three displacement fields, the east displacements, the north displacements, and the vertical displacements, and scale them, as I say, by their line of sight vector components, contributions. So we can do that, and that's pretty easy. You can plot them, and then you can add them all up, right? The sum of the three contributions is going to be the line of sight displacement in that line of sight direction. Okay, so we're going back to what we had before. We had a lot of north displacement, we had a moderate amount of east displacement, and we had very little north vertical displacement. If you go to here, though, you can see how much they actually contribute to the line of sight. So the north component, remember, we only contribute the line of sight vector component for the north component of motion is only 0.1, so you get 1/10 of what you started with contributed to line of sight. So we had about 50 centimeters of motion on either side of the fault, and now we have 5 or a bit less than 5 centimeters. So a very small contribution from that. But the east and the vertical components both have significant contributions compared to the north. And when you add them up, they have this interesting effect of interference with each other. So this is an interferogram that you would get for this earthquake, and it looks quite unlike what you might expect, I would posit. Like this is a north-south strike-slip fault, but you only seem to get significant displacement on one side of the fault in your interferogram. And the reason for that is that you're adding and subtracting basically the east and north components to each other, east and vertical components to each other. So on the west side of the fault, you get constructive adding of this positive displacement in line of sight with this one. You have negative displacements here that add to these. And so the net effect is to amplify the line of sight displacement on the west side of the fault. And then on the east side, you have positive displacement that cancels this negative displacement, more or less, and then negative displacement here that cancels this positive. And so you end up with very little displacement on this side of the fault. So this is an extreme case, but one of the interferograms that Anne showed yesterday in her sort of tour of InSAR theory was an interferogram that looked like this. And this type of modeling was very helpful to me, because that was one of my interferograms to try to figure out what on earth was going on, why all the displacement seemed to be on one side of the fault when we knew that the fault ran north-south. Well, it's because of this particular effect that the way that surface displacements resolve into line of sight can sometimes be complicated, and you have to sometimes think it through to figure out how to make these how to interpret what you're seeing.
Meredith, do you still have this little app that Oscope once developed? Is that still around?
No, sadly not.
Ah,
it was proprietary code that was bought. The company was bought twice, and so we lost contact with everybody that knew how to keep it running.
Yeah, so I use this notebook a lot because I think it's super fascinating to play around. I mean, you can change the modeling parameters here in that notebook to whatever you want, and it's often really quite enlightening and surprising, what kind of InSAR phase patterns you get from this. So it's often not very straightforward if there's lots of horizontal and vertical motion combined in an earthquake motion.
Yeah, so you can turn it to an east-west fault, and then maybe it looks more like you would expect. Now, lots of eastward movement, not much northward movement. Vertical movement is again at the ends of the fault. And when you project that into line of sight, then it looks very much like the east component of motion. That's because the largest motion lines up with one of the most sensitive directions of the radar. This kind of pattern is extremely common in earthquakes that you see on nice east-west faults. Like, I don't know, there are a few in Tibet that are oriented that way around, resolve really nicely into line of sight. Like the Meduo earthquake was one. Yeah, so like, as you say, this is good for playing around and seeing what you would expect to see. I have a different version of more or less the same thing, which just does the same calculation, but it also shows you the line of the patterns in both ascending and descending. So again, the numbers are more or less the same, but it's all in one place now. You can tweak your parameters. This is a north-south right lateral fault, I guess, with ascending and descending incidences and pointing azimuths defined and elastic parameters, and you can run this whole thing. And oh, did I forget to run what did I do? I forgot to run something. And at the end here, we plot everything. So you can plot X, Y, and Z displacements. You can plot the line of sight components and the total line of sight displacement. So this again is a very similar case to the first one I showed on the other notebook with a fault that runs north-south, and the major contributions to the line of sight come from the east and the vertical components. And this just goes to show you, if you had both ascending and descending, you end up with a pattern that reverses. I think it's plotting ascending before descending. I should double check that. ISCE, yeah. So it's the first row is the ascending and the second row is the descending, DSC. Yeah, and so you can see what you would get in both types of interferogram in this case. And the pattern reverses in terms of like where the displacement is. It's all on the west side here in the ascending and all on the east side in the descending. If you made this be a fault with a strike of an eastward strike, say, and run through all the plots, then the interesting thing that happens here is, you get a pattern which is dominated by the eastward displacements in this case, and the deformation patterns completely reverse, almost completely reverse between ascending and descending in that case, which is the mark of a eastward motion and between ascending and descending viewing geometries, that basically the satellite's pointing in the opposite opposite direction in the east-west plane, and so what did resolve as positive in one viewing geometry will resolve as negative in the other, and vice versa. And that's what you see here. So that's great.
There is a question in chat, and maybe either you or maybe Eric can answer this. It's like, what is the exact definition of the ICE azimuth and range angles that are provided in the output? Is there any documentation? Do you know that?
Somewhere buried deep in the scripts, it is mentioned somewhere. I think it's defined as the azimuth of the ground target pointing towards the satellite.
Yeah. So exactly what the coordinate system and reference frame is not always self-evident, and there's a little trial and error. But
it's super opaque.
but if you know of documentation and have a link or so, we could.
I found it once. I can't remember where, but yeah, maybe Eric could dig it out.
It's a very very good question.
I think
there's many things within InSAR standardization nomenclature is not clear.
Is it correct that ICE3 actually just gives you the three components of the line of sight vector rather than making you calculate it? I think it is, but
yeah, I'm not sure.
I remember having that conversation with Paul Rosen. Yeah, my understanding is it's the azimuth from the ground target pointing towards the satellite. But why they're given as two negative angles, heaven only knows. But yes, those numbers, if there is a you might have seen if you did all this processing that Eric was just showing. Let me see if I can find it. 2.1, right? In InSAR, in merged, somewhere in here, this thing called los.rdr.geo is an image which has the same dimensions and same coverage as your processed interferometric phase, and it has two layers, one of which is the incidence angles, and the other of which is the pointing vector angles for every pixel in your interferogram. So you can, if you can interrogate this file, you can find these two angles for every point in your interferogram. So some of the things I'm going to show you in a second, read this and load it in and assign it to your pixels when you come to downsample your data. Because you need to know, if you want to model your data effectively, you want to know this pointing vector for every pixel that you're trying to model. Okay. Any more questions on this sort of thing before I plunge further ahead? You were warned. All right, so the next thing I'm going to look at is this notebook called Quad Tree Decomposition. Oh, interesting that it doesn't want to resolve my render my titles anymore. I can put.
Yeah, it very much. Oh, it doesn't work either.
That didn't work either. Well, interesting. The new version of Jupyter Notebook is.
It very much favors Markdown over HTML.
Yes. All right. So what we're going to do now is downsample our data. So we mentioned before, I mentioned before, I'm sure that I did, that interferograms have millions of pixels, millions of them, and it is a lot to try and calculate the motion of every single pixel if you want to run a model. Especially when the data themselves are often very spatially correlated. You can look at an interferogram and see there are wide expanses of the data that have very similar values that do not really vary much with respect to the process that you're trying to look at. So you don't have to represent every single pixel if it doesn't add any more information. So one strategy that InSAR people often use is to downsample your data, which is to say, reduce the resolution of your data in certain areas that don't matter, and focus the sampling of your displacements in areas that do. And a very popular method for this is what we call the quad tree decomposition, which the way that those work effectively is to take draw a box around some area of your data, calculate the variance of the data within that box. And if the variance is above some threshold, which you can specify, it will divide that box into four equally sized smaller boxes and repeat the process again. And so what happens is that where you have variance in your data, you will focus on it with your sampling, and where your data are very similar, you don't. And in the end, you get this kind of more heterogeneous sampling of your data set, which is mostly focused on places where the data are variable and not focused on places that are not. And I wrote one of these once, and it was a bit of a pain to keep track of all the boxes and things. I'm really happy to see that there's a group in Germany have made a set of routines called Pyrocco that do a lot of stuff associated with earthquake modeling. And one of the modules in Pyrocco is called Kite, and this Kite method does quad tree sampling. So we will use it, and we will load it in. And it's there, so it didn't complain. It imported the Kite routines without problems, and a few other things, some plotting, some math, and some coordinate transformations and spatial information. Okay, so the first step here, hopefully this won't be as complicated as some people found it for the TopSap routine, is to download a load of interferograms and associated files. I say a load of interferograms, one interferogram and associated files. So you can see here we are downloading a geocoded unwrapped interferogram, where we're downloading that file I just mentioned. That contains the pointing vector information. We're downloading a water mask, and we're going to download the coherence information, or the correlation, I should say, .core here for correlation, which we can use to mask out noisy pixels from our data. Remember that Snafu, the unwrapper, which I used to make this interferogram, doesn't do the masking for you. So I am going to do it for myself. I see there is a question that's irrelevant to this to this exercise. Maybe this question should be asked some other time, or later. Anyway, so next I'm going to specify the file names. I'm going to give variables to all these things. The interferogram name, the correlation file name, the interferogram path, which is in the current directory. I didn't do a very neat and tidy job like Eric did in making subdirectories where I copy everything. My bad. The mask name, I'm going to use the water mask, and I am going to give this as the output file name. I should have said that this interferogram is of an earthquake that occurred in Turkey in 2020. Near the town of Elazig. It's also known as the Sivrice earthquake. It was a magnitude 6.7 on the East Anatolian Fault, and has been it and what happened after it have been something of an obsession with my group of late. But I was already interested in it 5 years ago. And this is a nice little strike slip earthquake for modeling. It's of a good size, that it has a good signal. It's suitable for this sort of thing. So I'm going to run this just to establish all these variables. A couple more things here. I'm going to input the radar wavelength of Sentinel-1. If you read the documentation for Kite, they complain that Sentinel-1 data files do not contain the wavelength anywhere for Sentinel-1. So they can't possibly read it from the files that we supply. So okay, I'm going to define it then right here. I'm going to define a correlation threshold of 0.25, and that's just really low actually. If data has a correlation of below 0.25, then it's almost certainly noise. but you could probably raise this higher and do something similar. And then we are going to load our data into our notebook. So if you run this code cell, we're going to use GDAL to open our interferogram file, and we're going to plot it. That's what this does. And here is our interferogram. Doesn't it look lovely? You can see some clear division between positive and negative displacements along a straightish line that turns out is quite close to the location of the fault. And people who are, do I want to make sure I'm using this kernel? It worked though, didn't it? Yeah, you want to make sure you're in the Python conda env thing for those two of you, Mara and Carthy. That could be your problem. You might need to change the kernel you're using. Okay. So there's our interferogram. You can crop it if you want to. In this notebook allows you to, but I'm going to keep the whole interferogram because it looks good. But I am going to do some other things. I'm going to load in correlation file and the line of sight information and apply a watermask for all of this. And also some other stuff, some load in from the interferogram, some geospatial information like the reference location of the interferogram, which is the northwest corner usually of the interferogram, the pixel size of the interferogram. And I'm also going to convert from interferometric phase to meters by by multiplying the interferogram by lambda, the wavelength, divided by 4 pi. And that way then we'll have a bunch of estimates of the surface displacement in line of sight in meters. Okay. Did I skip something? Did I? Oh, I just changed kernel, didn't I? Yes. This is the thing that Eric mentioned earlier, that if you change the kernel, then you have to rerun all your what's going on? Load. And then run this one. If you manage to do all that, this is populating some of Kite's objects. With the Python kernel, you need to make sure you're using exactly the right one. Otherwise, it won't work. Python, conda env, earthscope, InSAR. Work for me. Okay, so this then is what's now been imported into Kite. So I've applied a water mask. It's masked out all of these watery things. This is the Euphrates River. There's some reservoirs, Lake Hazar. They're all gone. And you can run the quadtree decomposition, and that's as simple as running this command here. Qt equals sc.quadtree, and it does a bunch of thinking behind the scenes. And when it's done, all right, we have some choices to make. And I provided what I think are the appropriate set of parameters here. You can choose your variance threshold. This is 0.02 meters squared that I'm going to try and use here. The number of not numbers allowed in your data set. So all the stuff that's blanked out here is nans, right? Not a number. If you if you make this threshold too small, if one of your quad tree boxes has a lot of nans in it, it will divide it into smaller boxes so that you minimize the number of nans in the box. There's not a lot of benefit to doing that because it's just going to focus sampling around places where you don't have data. So you could typically you want to make this number high. This is like a fraction. So this 0.5 means half of the pixels within a box could be not a number. That should be fraction, not percentage. I won't remember, but but there you go. The other two things are the maximum size of your quad tree boxes and the minimum size of your quad tree boxes. This is in the units that you're using, and my interferogram is in degrees, latitude and longitude. So my maximum tile size is going to be 0.2 degrees, which is about 20 kilometers. And my minimum is going to be 0.01 degrees, which is about 1 kilometer. Okay, and if you run this, then it will tell you how many pixels you have sampled your interferogram down to, or how many data points you're going to have. And you're going to have 194. So we started with I didn't check how big my interferogram was. I guess I could do that by running the command whos, and it will tell you all of my interferogram is 5,000 or nearly 6,000 pixels by 5,000 pixels. So what's that? That's like 30 million. 30 million pixels. That's a large number. I turned that into 200. Go me. The concern is always, of course, that you might have like thrown something out that you didn't mean to, or you might have made your data unnecessarily coarse. We can look at that in a minute. But anyway, what else can we do? We can look at all the quad tree, what it calls leaves in Kite, which are the boxes and where they are and how big they are and what the value of the pixel with the value of the data within them is. And you can also plot them, which is probably more meaningful. And this is what the quad tree decomposed interferogram looks like. It doesn't look so bad to me, to be honest. It reduces we can see where the fault is still. There's a sort of, it's trending through here, and you can see in the far field where there's very little variation, these uniform areas very similar to each other, and really it focuses a lot of the sampling in this area where there's obvious displacement due to the earthquake. So I'm going to say that's good. You can obviously do things to make it more complicated. I would advise you not to do that right now because we all want to be using the same data set when we come to do our modeling. But just for the purposes of demonstration, if you were to change the threshold of the variance and make it want to sample even more finely, because now even a very small variation is going to somehow exceed that threshold, then what do you get? Well, we'll see. Well, you get a much more focused sampling. Okay, so you can do that sort of thing. You can play around. I'm not going to do that here. I'm going to go back to 0.02. But you have some leeway to play around with these parameters if it's going to be your own data that you're going to model to see. Whoop, 0.02. And when you come back down here, oh, that's an annoying large number of points. You get back to this. One of the reasons why you might favor a model which is more coarsely sampled than you could have is that every time that you run a model, an inverse model using this data set, it has to calculate the displacement of every single point. And the more points you have, the longer it takes to do that. So minimizing or reducing the number of data points you have speeds up your computation, sometimes dramatically.
And if there's a question by Camillo, and I'm not sure if I quite understand it right. I'm not sure if you see the question.
How does this information translate to having an array in Python? If you load this downsampled image, all pixels will have the same size. No, this is actually like a vector data set.
Yeah, it's more as a sparse grid of data.
Yeah, it lists that if you look at the SC, which is the Qt object, which is what this Python function is called kite is producing. It has all these I can't remember what they're called, classes. My knowledge of
Objects.
objects. They're objects. All of the objects. So like this leaf object contains all the locations of all of the sampled the
But
sampled
it's no
points.
longer a evenly spaced array.
Well, this is. I mean, it's literally just a list of like the coordinates and the dimensions of these boxes. It's not representing every pixel anymore.
Yeah.
And Camilo, you'll see, I think, in the next notebook a little bit more about how this is used in modeling. But it's not an array in that traditional sense anymore, where you have values in equally spaced gridded points.
Right. You know the corner locations of these boxes, the sizes of these boxes, the average value of the pixels in those boxes, and you've kind of tossed out all the pixels. And what we're going to do now is extract the center points of all those boxes, convert them to a UTM coordinate system, so that we can use it in a Cartesian grid of points, which is what a Carder can handle, and output them. Along with the other thing that the quad tree decomposition routine will do is ingest the line of sight information, and we want to output that for every point as well. Yeah, so this is just telling you what the reference point of your data is, and it's doing everything with respect to one corner of the data set, so we need to know what that point is, and it's whatever that is in latitude and longitude, and we can convert that lat long coordinate pair into the corresponding UTM coordinates. So I have done that. And now we are going to convert the positions of all the data points of those boxes into UTM as well. And here you can see we are going to extract the thetas and phis from those boxes, which the quad tree routine has nicely sampled for us, and turn them into the line of sight components for each data point as well. And I do some messing around with the data sets because traditionally in the olden days, all of my modeling codes used coordinates in kilometers. So I convert my XY coordinates into kilometers as well. And then we can actually plot where these points are in actual UTM coordinates. And there they are. That's my sampling of my interferogram. Now, instead of showing it as boxes, I just show you the point at the center of each box, color-coded by the displacement in meters. And the final step is to output this. So we can save these into a file. And you can also output this in the internal format of Kite if you want to. And I see there's a question, is quad tree similar to some kind of clustering? It is a method of image compression. Like some image compression uses this because it basically retains information where there is information and kind of throws out data where you don't need it. I don't think it's clustering per se. It's more like directed spatial averaging. Anyway, the whole point of this was to produce a data file that it will have outputted called alazic ask.okinv. you can open that file and see what's in it. What you have are 7 columns. The first column is the x coordinate of your pixel. The second coordinate is the y coordinate. The third column is the data value for that place. So this particular data point has a displacement of 0.022 meters or 2.2 centimeters. And then the next 3 columns are the 3 components of the line of sight vector. So 0.65, 0.11, negative 0.74, and there's a label in the final column. And there are 194 of those because that's how many leaves we found when we did our quad tree decomposition. For the purposes of the exercise we're about to do, it would be great if everyone had the same file, which you would get if you used the same numbers that I did for the thresholds and things. So make sure that you did that. 0.02, I can't remember what they were. You can see them all the way up here. Oh, I never reran that. But yeah, there should be 194 leaves with these values. Okay, so if everyone has that, we can try and take this data set and model it. A few things we're going to want to try and do before we start is to try and figure out some of the a priori inputs that we would put in our model. Usually we're going to use an optimization algorithm, which is going to play around with different combinations of model parameters until it converges on a solution that fits the data well. But to stop it wandering off into the distance, we apply bounds to the estimated parameters so that they don't get too crazily different from reality. So one of the things we're going to want to know is what the strike of the fault is. What angle does the fault make with north? I'm going to say it's going to be something like 60 degrees. I don't know. This line has like an angle of about 60 degrees with north. You also have to eyeball how long the fault might be. And I'm putting my fingers up against the screen, and I'm thinking it's probably somewhere in the range of 40 kilometers. If this is 40 kilometers there. And then you have to kind of also eyeball the sort of the center of the fault as your starting location for the fault, and that's 490 something, 42, I don't know, 30 something, somewhere in here. You'll see what my guess is in a second. But we're going to open this notebook called Okapi Optimization. I don't know if that's its full name, something like that. And this makes use of a Python script called okapi.py, which you can open too, which basically encapsulates all that stuff I did with the Okada subroutine, rotating their coordinates and projecting them into line of sight. This does that, but it's just bundled into a couple of routines that you don't have to think about anymore. Rect shear fault for rectangular shear fault. It takes as inputs fault parameters, elastic parameters, and data. In this case, the data point locations that you want to calculate points for. There's also a version of it for tensile faults, which is to say dikes. You can model dike intrusions with this. And there's also 2 functions that calculate penalties, which means that if you input the data and it calculates the displacements, it will calculate also the misfit, the penalty. High penalty means that you didn't fit the data well. Low penalty means you do fit the data well. So all of that is bundled in this Okapi Python script, which we will use, but we won't look at it anymore. And see, for now, it's going to import those Okapi things. I'm going to make sure I'm using the right kernel. so it doesn't complain. I was able to get it to import. Great. So the first thing we're going to do is read in the data. Just going to load it in to NumPy. The second thing we're going to do is define our initial model. So I mentioned I was going to guess the strike was 60 degrees. Okay. I might actually make my dip bounds a little, well, make them 20. So the first number is your initial guess of the parameter. The second one is the uncertainty, or rather, it's going to set bounds that are 2 times this, a bit above and below the central value. So like you have 2 sigma confidence intervals. That's what this is. So this means if I put the value of 10 here, the strike could vary between 60 minus 2 times 10, which is like 20, to 60 plus 2 times 10, which would be 100. So that's a very generous set of bounds. Similarly, you can make the dip vary between, say, 50 and 130, which means actually the fault could be dipping either way, to the west or to the east, between 50 degrees each way, which is a lot, but maybe that's okay. I'm also giving a generous estimate of the bounds of the rake, which is the angle of the slip vector within the fault plane. 1 degree is basically almost pure left lateral, but we could have 20 degrees of motion, of the thrust motion or normal motion, sort of bundled into that. If it doesn't mean anything to you, that's okay. Don't worry. There's the rake parameter is something that earthquake seismologists sort of obsess over and no one else considers very much. Slip can vary by several meters as well. That's good. We have the X and Y coordinates of the center of the fault projected to the surface. I kind of eyeballed that earlier, and that's close to the numbers I came up with. Again, if you're nervous, you can make these bounds larger. The along strike fault length, I estimated about 40 kilometers. Here I put it at 35 plus or minus 2 times this. So it could be somewhere between 25 and 45 kilometers. The top depth could be between 0 and 8 kilometers, and the bottom depth, was between, well, anyway, the bottom depth can be as great as 22 kilometers. And you establish a bunch of arrays with all these numbers in them. So the starting values are all the ones from the left, the sigmas are all the values from the right, and the higher and lower bounds are 2 times that from the starting values. And then you can randomly select a value that are within these 2 bounds as your starting model. So that's what that's going to do. And it will do some shuffling of your parameters. If it turns out the top of your fault is below the bottom of your fault, then it will flip them. And that's what this all does. So in the end, I come up with a starting model, which is whatever this is: strike, dip, rake, X and Y coordinates, and the length, the top and the bottom depth. My top and bottom depth are really close to each other. So this is a very long, skinny fault, which may or may not be a good starting model. But anyway, you can then establish your elastic parameters. And okay, we have gone to the point where we have we've input all our guesses and our bounds. We've selected a model from that space, basically using a random function to figure out some estimated values. And we can calculate what the penalty, which is to say what the fit of those calculated values would be to the data. And I'm guessing it's not going to be very good. Right, so I get a penalty of 1 square meter squared. Yeah, 1 square meter. Okay. So that's calculating the displacement for every point of those 194 points that I selected using the quad tree. And This question is coming in. Dip cannot exceed 90. No, dip can exceed 90. It just means it's dipping in the opposite direction. In this case, so if our initial model was for a fault that dips, a strike of 60 degrees would imply a dip to that's at right angles to the right of that, which would be a dip to the sort of the southeast. Then a dip of greater than 90 would actually imply the fault was dipping to the northwest. So that was a live question. Why are you saying that the fault can dip more than 90 degrees? Well, it can mathematically, actually, in the Ocado routine. When you have a dip of greater than 90, it means the fault is dipping the other way. Okay. So anyway, your penalty is whatever your penalty is, and usually it's bad. I'm hoping for values that are more like 0.1 rather than 1. So this is maybe 10 times larger than a good model. So we'll see how we do when we use this as the starting point for an optimization. So for this, we're going to use a function that's built within SciPy, which is a Python library of scientific computing things, called optimize minimize. And what this uses is an algorithm called the Powell algorithm, which is a downhill direction set algorithm. So what it does is it tweaks parameters in combinations that allow it to traverse misfit space until it finds a minimum. We always think about optimizations as you're sitting on a landscape. This landscape is your penalty function, where the bottom of the landscape, the lowest point, is the location of the best model, and maybe your coordinate directions in your landscape are some of your parameters. In this case, we have 9 parameters that we're solving for, so you can't really think about things in 9 dimensions. I mean, I can't. But if you think about 2, I mean, this concept is scalable to as many dimensions as you have. It's just that human brains think of things in terms of X and Y and vertical. But what it tries to do is to figure out which directions lead to the fastest decreases in misfit, which were the steepest ones for going downhill. And it tries to find its way to a point where you can't go down anymore. Find to the bottom of your landscape, the lowest point. And you have to also, one of the inputs you need is to have a starting location, right? You can't just do this. You need to start somewhere and find your way to the bottom. So that's why in the beginning part, we chose a random set of parameters that were within our bounds. The only problem with this is that, well, we'll see in a minute. All right, but that's how this works, and it's pretty easy to run. Actually, you just have to set up all the things, but we have set them all up. So we're going to use this thing called minimize, the optimize minimize function. We're going to establish our bounds as a bounds object for this algorithm, and you can run it, and it will take a little while as it's computing. Each time it tries to tweak the parameters, it has to recompute the misfit. So it's doing that a load of times. It took a few seconds. Okay, and this is the output that I'm displaying here, and it tells me that my operation terminated successfully. That's good. It was success. True. And now my penalty function is 0.147. It started out as 1. So this is better. It's better by a factor of about 7. Okay, so we've improved our model a lot. These are the values of my model parameters that it output. And this is the number of times it ran the penalty function. So it ran Ocado 6,383 times to get to this improved model. So this is why it's good to make your computation time as fast as possible, because that's 6,383 times. Well, it took a few seconds, but if I doubled the number of data points, it would have taken double the amount of time at least to do this. So yeah, you can you can run this and it'll output what all your parameters are. So I get a strike of 63, a dip of 129. So dip is actually to the north and not to the south. Get an estimate of rake, I get an estimate of slip, and all these things. So what I've done here is run one model, and I imagine if you all ran a model yourselves, you would get a different answer. Can anyone confirm? I get different answer values without changing anything. Is there a random component to it? Well, yes. So what we did right up here is to calculate a random starting position. So a random selection of parameters from within the bounds that we have specified. That's kind of baked in. So yes. Did anyone find a better misfit than me? I got a misfit of, well, yeah, let's extract my parameters here and paste them into that cell down there. So my penalty function, my best penalty was 0.147. So I'm going to paste that here. And my parameter values are these things here. I'm going to copy and paste those as well into here. Ugh. I need to put some commas in because this is a NumPy array and it likes to have commas. If everyone could do this with their results, that would be fantastic. And it sounds like people are getting different things, which is also good. The randomness is supposed to be a feature. Is that all of them? Is this gonna be happy if I do that? Okay. So in a normal optimization, what we're going to do, what you find when you run this is what we call a local minimum in your penalty landscape. It could be the bottom of the nearest valley to you. You could imagine if you were trying to find the deepest crater on the moon, and you just used a downhill method, that you keep walking in a direction until you find yourself at the bottom of something that you can't get up of, that you would find the bottom of the first crater that you come across. There could be a crater that's beyond the one that's closest to you that is deeper, but from your starting location, you won't ever find it because you just go downhill to the bottom of the nearest one. So the reason that we randomize our starting location, our starting parameters, is that potentially if you try enough different random locations, you will find the deepest one if you repeat this process over and over again. So what I have done for you all is I've made a spreadsheet. Now I need my chat window, and this spreadsheet here, which is located here, and there is a space for you to type in your name, to paste in your penalty that you just found. Where did I put it? Here, 0.147, blah, blah, blah. Be careful not to paste over everybody else's. And then paste in the string of model parameters that goes with it. So this thing. Because what you can do when you do this is yes, you should randomize your starting location. And this notebook has that capability built into it, that it will run 100 times from different random starting locations, this optimization. But as you saw, it takes a few seconds, 5 seconds, to run the inversion. That means you would take 500 seconds to run it 100 times, which is going to take a long time. So instead, since there are a load of you out there running this, we could solve the problem by crowdsourcing it. You all have to run it once, and we can get the hive mind, the collective's best model out of this. So please all populate this spreadsheet. And we'll see what we get. The value stopped coming in. Looks like Sophie is the current leader. I guess that's all we're going to get. How many people are on the call? People who can see that? Crickets. No one is speaking to me anymore. Yeah, I think Sophie's might be the best. 0.85 is I think my current leader, unless someone can see anything better. I see 0.88. Of course, people with spreadsheet skills can actually sort this. 0.8588. Oh, if Blanca is can give her answers, that might be the best model yet. Sorry, Sophie, you've been superseded. But we need your parameters, otherwise the model doesn't exist. We need so Blanca, we need them in the form of a vector, like this. If you saw, I copied and pasted the numbers from up here. I copied these and then put them in a vector down here. Those are what we need. Oops. Yeah. So if you could do that. Still waiting for them here. Come on, I need them in this form. An array, a NumPy array in square brackets with commas, please. I'm still waiting for Blanca, who looks like she has the best model. But she needs to share those parameters, otherwise she doesn't win the prize.
Yes, 1 minute.
Because we want to use this as our best model. And Baruz, who's in second place, also hasn't got them in the wrong format. The suspense is killing me. Now her penalty's disappeared. Give you 10 seconds before I give the prize to someone else and look at a different model. It's not supposed to be this complicated. There should be 9 numbers. Meanwhile, someone is reformatting the spreadsheet whilst other people are trying to enter things, which doesn't seem like a good idea to me. Well, let's see. So Balruz also did not enter his model parameters correctly either, so I can't use his. So I'm gonna go with Thapper. Thapper is the winner because he's the only one who actually gave me all the things I wanted. I'm going to copy those parameters into here now. So the best penalty for the purposes of this will be 0.000851. And then, was there not a full string of parameters there before? Where have they gone? Seriously, you people. Could you just stop messing around and give me the set of numbers I need? All right. Jeffrey, your numbers are like correctly formatted, so I'm going to go with those. And oh dear. What's going on? Best fault parameters are these. Best. Was it best penalty? I somehow deleted that. It's too late, you people. You're doing it all wrong. All right. So those are my best penalties, my best fault parameters, and you can plot these and see how well they fit your model. So on the left here is Jeffrey's model. So on the left here, sorry, is the data. In the central column is the model. And on the right is the difference between those two. And you can see that we do a reasonable job of fitting most of the features of this data set. Like there is obviously some complexity in the deformation pattern, which we're not quite capturing. The fault has a bit of a kink in it, maybe. There looks like there's a couple of clusters of blue points, suggesting there are a couple of places where slip is concentrated on the fault that we are not capturing because we're only modeling with one rectangle. But it's a pretty good fit, all things considered. And, you get something which a residual of 0.08 is really, really good. So that would be your way of doing this modeling is find 50 friends and tell them all to run this model at the same time. Of course, you might not have 50 friends. So the other thing you can do is to run this code cell here. With what it does is it defines a best penalty function of a very large number, and it loops through 100 times. It finds a new starting model every single time, new random starting location. It does your quality check. It specifies bounds, and then it runs the Powell algorithm. each time it will compare the output penalty to the best penalty that you've seen so far. And if your penalty is better than the previous one, then it will save those parameters and that penalty and start again. So it loops 100 times, and this takes a while, but you can run it if you want, and you will see over time, maybe it's taking a while to run the first one. Yeah, you'll see hopefully the penalty come down, but you'll also see why I didn't get you all to run this, because it takes ages. Oh, you see, after 2, the penalty's already come down to close to what Jeffrey's was, but it might continue. It might find a better one, but it will take a long time. So I'm not going to talk about it anymore. I'm going to stop. So yeah, I don't know if there are any more questions about how this works or what we've just done. I did want to talk about, though, briefly, what the homeworks are for today, because we have come to the end of today's program. There are 2 things. So one is using a copy of the 2.1 notebook, process your own interferogram of somewhere else. And save the notebook as a PDF once you're done to prove that you did it, and upload that to Moodle in the spot for the homework for 2.1. And the second homework is to use a copy of the notebook I just showed you and your own and the one on quad 3D decomposition, and model a different earthquake. And there are 2 options there. One is to process your own interferogram of an earthquake. If you have a recent earthquake that you like, it's usually easier to do smaller ones than larger ones. So anything in the range of about magnitude 6 to magnitude 7 works well for this, with one square, well, with one rectangle fault. I also have instructions on how you might go about downloading other data. I have uploaded at least one more interferogram to an AWS bucket that you can, and given some instructions on how to get hold of those data to do the decomposition and everything yourself. But the thing you also want to start with doing is making copies of all the notebooks to a different directory, and then downloading some data or processing some data and copying it across so that you can run the notebooks on that. How does that sound? And where has everyone gone? I've not heard any voices in ages. But I know you're out there, people. If you want to model small earthquakes, then you're not going to detect them below a certain size. It's below magnitude 6, it gets a bit tricky. You have to be quite lucky to capture a magnitude 5 earthquake. It has to be extremely shallow. So Stephen, that was what Stephen was asking. What about modeling small earthquakes? Basically, unless you know that you're going to get a signal, it can be tricky. I have a paper from a few years ago where I tried to look at every magnitude 5.5 earthquake and larger, and some of the 5.5s were indistinguishable from atmospheric noise, which is another problem. Like once they're a certain size, they can be overwhelmed by noise quite easily. And if they're deep, you might not even see the deformation from them. So you're best to stick with magnitude 6s that have source depths of 10 to 15 kilometers or less. Then you have a good chance of seeing them.
I think I have seen an interferogram of a magnitude 4 earthquake, but it was like 1 kilometer depth. So it came right to the surface and there was a clear surface break.
Rowena showed me an interferogram of a 3.5 in a quarry, but I think the source depth was like 500 meters or something.
Yeah. So if it's right at the surface.
But you're going to be processing hundreds of interferograms before you find one of those. The fact that we know what the smallest ones are means that, you know, they're famous. Yeah, there's literature like of like 4.4s, 4.9s. 4.9s, I think there are a couple, but you have to go looking really hard for them. And I don't know how many 4.9s happen every week, but lots, dozens, and we don't see them. Okay. Anything else that anyone wants to clarify? I think you have your marching orders. I'm quite happy to stop speaking.
We are over time anyway.
We are. No one stopped me.
25 minutes.
My bad.
I was giving you warnings.
No one was saying anything. Once you're presenting, you can't see. I mean, I saw the Q&A, but that was about it.
Tomorrow I will make sure that everybody knows. I'll play the music.
That would work, or some kind of like final countdown music or something. You know.
We didn't stop you because we were enjoying your lecture.
There you go. See, my people love me. Yes. Anyway, tomorrow you can hear from some different people who might stay on time. And we will have office hours this evening if anyone wants to come and talk about modeling or issues they've been having. But other than that, I will see you tomorrow. Have a good rest of your